Tomatoes?
Hello, welcome to the video for what is simple little example class. You can go down here under controller. Not physically possessing control over it, so therefore there's no reason to keep that in there. Now if you were going to have something, for example, where it's a AI controller when you're not physically possessing it and then you allow your player to possess it, then you would have two different controllers and you would swap in and out between the AI and the player's controller. So right here we have get controller. The node is basically going to get the controller that's attached to this pawn. And if we look in our class defaults and we scroll down, we're going to find our controller class for the AI is AI controller or generic AI controller. Either one of these will work. AI controller is the default that comes built into the engine. Generic AI controller was the one I created. Now if we go and run this, you'll notice our pawn works. Now to show an example of what I meant by it needs to be an AI controller, if I switch this over to a generic player controller or player controller and hit play, you'll notice the pawn doesn't move. The pawn is trying to move, but because the controller attached to it is not an AI controller and doesn't have these components, it's not going to work properly. So make sure you have an AI controller parent for the controller that you have hooked up to your pawn that you intend to be controlled by the navigation system or the AI nodes. So there's our controller setup. The next one is, where are we going to? Now the simple move to actor takes a actor as the reference for the goal. So I'm doing this pretty simply. I'm getting the player's controller, getting the controlled pawn that the player is controlling, and feeding it in as my simple move to. So as you can see, when we run it, he's moving to that one. And that's why when we run it and we move our character, you'll notice he's trying to chase it down. And once he gets to it, he finishes. Now here's one thing that the simple controllers, the simple move tos, do that you may have an issue with, and why this is the basic form of AI. Let me go ahead and hook up my print string here. And you're going to notice immediately when I hit play, before my pawn, my AI, gets to my character, it's actually going to print out the string. See how on the top left it says moved? This is an execute without a delay. It's going to execute the move to, and then it's going to print the string immediately. It's not going to wait till it gets to the destination before it actually continues executing. So that's something to keep in mind. The simple move tos are literal go here, and then it continues on with execution. Now, looking at the simple move to location, it's going to be the same thing. We're going to want our AI controller for the controller, and then you simply take in a vector 3 or a location for the location. And in this case, I'm doing the same thing I did before, getting the player controller, getting the controlled pawn, and then I'm getting the pawn's location and setting it. Now, the difference we're going to see here is once I move, our pawn is still going to go to where it wanted to go to. And if I was to play it again, and then if you watch where the pawn's at and then I move, the pawn's going to continue going until it gets to the actual location. So it wants to go to where my player's middle point is, the origin, because that's the location I told it was. And if something gets in the way, for example, another pawn's there, it's going to continue trying until it can finish the simple move to. There's no failure. And to show that's the same thing, when we hit play, you'll notice it says moved immediately, even though it hasn't reached its destination. Now in terms of using this for a basic AI, you can technically cheat. Let's go ahead and unhook our print strings, and we'll do the move to actor event. We're going to hook this back up here, and we'll hook it up into a timer. What we're going to do here is basically, we're going to tell it to move to the actor, and then every 4 seconds, we're going to call this event again. So what we're going to see is it moves to the actor, and then it's going to move to the actor again, and then move to the actor again, and it's going to repeat every 4 seconds. This is pretty much your most basic event again. So we're going to tell it to move to the actor, and then every 4 seconds, we're going to call this event again. So what we're going to see is it moves to the actor, and then it's going to move to the actor again, and then move to the actor again, and it's going to repeat every 4 seconds. This is pretty much your most basic, simple AI. Now you'll also notice the orientation of our AI is rotating appropriately for the move. We're not just simply moving along whatever rotation it's currently at. It's rotating to face our target, and it's moving to our target appropriately. So that's one benefit of our simple move tos. Now in terms of actually using this, it's useful if you want to move something maybe along a patrol point, and maybe somewhere in the actual AI itself and your pawn you have some form of sense every frame or every half a second. Maybe it's doing a line cast, or can it see the actor every half a second in addition to this? But one thing you're going to have an issue with, as you notice, because you're firing the simple move to and there's no escape on it and there's no abort, you might have a slight bit of an issue when you're trying to do something more complicated. And that's where our behavior trees, our blackboards, and our other more advanced AI come in, and those are covered in other videos. But for now, this is just a simple node for simply moving an AI pawn, to an actor or a location, simply. Now, a useful use for this is maybe you want to simply move a bullet to a target, for example. You have a shooter and you're firing a bullet, you can use these. As long as you're not doing it too much, because this is going to use processing power, it's a really really easy way of just simply having something go from one spot to another appropriately. Just think of it that way. Maybe you have a homing bullet or a homing missile, and you simply want it to get to the end target, and there you go. Maybe put a little collision check in here where if it collides with something else, it explodes. And there you go, you have a homing rocket. So that's it. Those are our simple move to location and move to actor nodes. One thing I did not cover is because these are using navigation, I just realized it now, I forgot to mention it, you need to make sure you have a navigation mesh set down. You have a navigation bounds. And that's our little green thing right here, as you can see when I toggle it on and off. I've covered the navigation mesh. It is in another video. But just to show you, if I delete it, that would be that one. And then the recast version of it. And I go ahead and hit play, you'll notice nothing's happening. It's not going to work because we don't have a nav mesh. So you need to make sure that you do have a valid nav mesh set up inside of your scene, or else your AI will not be able to properly navigate to its target. So that's it. If you have any questions or comments, please feel free to leave them below.
Überall steigende Preise, steigende Benzinpreise, steigende Strompreise, alles wird teurer und die Menschen fragen sich, wie...
Tomatoes?
Hello, welcome to the video for What is AI? The Blackboard. So let's get right into this. This is just a simple overview of what the Blackboard is and what it's used for. It is part of the behavior tree. It's part of our basic AI in Unreal Engine 4. And all of the individual nodes for the behavior tree and the Blackboard will be covered in a separate video. This is just a basic overview of what the Blackboard is and how we would use it. So let's get started. So our Blackboard. You can access our Blackboard under the Artificial Intelligence section, Blackboard. And if we were to go ahead and pull it up, you're going to find it is blank. You only start off with a couple options on your toolbar, the add key option, and then your Blackboard details itself. Now, since you can have multiple Blackboards, you can go ahead and use inheritance with parent and child. So you could, for example, select another parent Blackboard, like my generic one I've created, and it's going to go ahead and inherit the keys from that. Now, if I go ahead and reset it, and then delete my self actor, we're back to our generic Blackboard. So that's something useful to keep in mind if you want to have Blackboards inherit from other Blackboards. Now, what is a Blackboard? It's a blackboard. It is a chalkboard. It is a piece of paper where you store stuff. That's all it's used for. It's intended to allow your behavior tree to read or set values that can be used in your behavior tree. It's as simple as that. So part of your behavior tree, maybe at the top, will be to find where your player currently is. And another part of it may be determining if your player is even alive. Now, another part of your behavior tree may need to actually do something based on that, such as if your player is alive, go ahead and move to its location. Since these are separate parts, these are separate tasks, or decorators or services in your behavior tree, we need somewhere general to store them, and that's what the Blackboard is. It's really simple to use. You basically, new key, choose your type, let's go with a bool for example, and then you name it. We'll go with like, is player alive? And that's it. You now have a Blackboard key called is player alive, and you have the following various entries. The name of it, a standard description, the type of the key, and whether it's synced on instances of the Blackboard. So if you create more instances of this Blackboard, for example, different AIs, you can use the instant sync to keep it synced across all the different instances. So that way maybe you have one general Blackboard value called active, and it's synced across all your different ones instead of having to set it individually. So that's what the instant sync is for. And that's it. I can go ahead and add another one. We can name an object like player object, and you're going to find it's the same settings. This is all the Blackboard's for. It's just to simply hold a value. Bools are going to hold bools. Objects are going to hold a generic object, so an actor or blueprint or something like that. You have your different other types, classes, floats, strings, rotators, and etc. And that's it. That's all our Blackboard is used for. It's just a container to hold values that are used inside of our behavior tree. So for example, let me go ahead and delete these values. And this is our new Blackboard data. Let's call this one test Blackboard. Okay. And let's go ahead and let's create a new behavior tree to show this an example. So we'll create a new behavior tree called test behavior tree. Now if I open up our test behavior tree, I need to assign a Blackboard to it. So I'll assign it to our test Blackboard. Let's go ahead and drag it off of here and let's create a selector. We're going to add a decorator on top of this called Blackboard, and we're going to go ahead and basically, if something is set, we want this selector to run. Now, if we go over here, you're going to find none. You have no Blackboard keys. Because the assigned Blackboard has no keys, we can't actually use any keys inside of our behavior tree. So this is why I was saying your behavior tree needs the Blackboard, because your Blackboard holds all your values. If we were to go into here, add a new key, we'll call it bool. Let's do this is player live again and save it out. We go back into our behavior tree. Now in our decorator, we have a Blackboard key is player live, and we can go based on if it's set or not. And that's it. That's what the behavior tree uses the Blackboard for, and that is what our Blackboard is for, holding values. Maybe inside one of our tasks, like let's say for example I have a service here. I've already created one, so let's throw this in here, called is player live. In here, you're going to see our player live has two variables that we set. One's called is player live, the other's called player object. This is what I name them internally inside of our service, right here. This could be called whatever you want. One of the things I noticed was trying to keep things consistent. So for example, if your Blackboard variable is, this is the wrong Blackboard, let's open up this one. If your Blackboard value is player live, then setting your variable inside your service to is player live makes it a little bit easier when you're trying to assign things, because it's really simple. Is player live, set is player live. You can also really easily see here an error. I have a player object variable I need to set, and inside of here, my player object variable is the location of the player, and it's a vector. But the problem is, inside of my behavior tree, this is my wrong one, let's close that. Inside of my Blackboard, I don't have that value. I don't have that variable. So inside, I gotta start, there we go. Let's make things easier and close everything down. There we go. So inside of my behavior tree, when I'm trying to assign this variable to a Blackboard value, it won't let me. So that's what your Blackboard is for. It allows you to transfer from this blueprint, this event graph, this service, the value I've assigned here, to a value inside of your Blackboard. So without the Blackboard value, for example, I need to add the new key now, and we'll do this, we'll call this one, I'll show you how they can be different, player location. If we go back to here, I now have a Blackboard vector called player location. I now can go into my service and change my player object to be player location. So now whenever the player object is set, which is right here, it's going to set the player location Blackboard value, which is right here. Now it seems a little complicated, and once you watch the videos that discuss how these are used, not just why we're using them, but how we're using them and the different ways of using them, it'll hopefully be a little more clear. But to sum it back up, Blackboard holds values, behavior tree sets and reads those values inside of services or tasks or decorators. That's it. So like for example, to show it in task form, we'll do a move to, and you'll see move to player location. And this one's actually pretty simple. If our player live set, we're going to go ahead and update our player location every half a second, and then we're going to tell the AI to move to that player location every half a second. So I mean, this is another simple basic AI and an example of how to use our Blackboard and what it's for. If you have any questions or comments, please feel free to leave them below. Bum 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 bum. Welcome to video 4. What cover this example? First, let's cover the behavior tree itself. This video is going to be slightly different. I'm going to cover the basics of a behavior tree, and I'm going to show you an example of one working. I'm not going to cover all the individual parts in this video. There are individual videos for each part of a behavior tree. We're going to cover what is the behavior tree and what. Now, technically this is an unworking behavior tree because I have nothing hooked up, and this is more for an example. So, a behavior tree. To access it, you can right click anywhere in your content browser. You can scroll down to artificial intelligence and click on behavior tree. And it's going to go ahead and, well, actually let's go ahead and do that. And I'll show you a blank behavior tree. It's just simply going to start with the root. The root is where we start off, and the root is basically where your execution begins. A behavior tree is going to go from the top to the bottom, and it's going to execute from left to right. So let's look at our example behavior tree here. So we have our root. Now the behavior tree root itself only really has one reference. It's going to reference our Blackboard object. Now our Blackboard object will be covered in detail in another video, but for basic simple explanation, it is an item that stores references to other items. In this case, I have a boolean called isPlayerLive and a player object, which is a vector that I used in order to actually record where the player is currently at. The Blackboard is just simply used to hold information, and it is where you access and store information when you are needing information in the behavior tree. It's kind of silly to say it like that, but it is literally a Blackboard where you store stuff and the behavior tree plays with it. So how would this work? Well, we have 4 primary nodes in addition to our root node for our behavior tree. We have our root node here. Then we have what is known as a composite node. That is going to be one of these gray nodes that we see here. We have a selector node, a sequence node, and a simple parallel node. In addition to that, we then have what's known as a decorator, which is our blue node here. And then we have a service, which is our greenish blue node. And then we have we finally have our task, which is our purple node. Now if I hook this up, you're basically going to see why this is called a behavior tree. You're going to start and it's going to fall down, and they call these like the leaves, and you have like your branches, and your basic flow is just going to flow down. In this example here, for an overview, basically once it fires off, the root goes to whatever it's connected to. Now the root can only be connected to one thing. The root only allows one connection. So below that, we have it going to our selector. Our selector node will be covered in more detail in another video, but it basically executes their children from left to right, and these are their children, and if one of them succeeds, it will stop executing. If one of them fails, it will go on to the next one, and it will go on to the next one. If all of them fail, they all fail. If one of them succeeds, it stops and it will not do the rest. Our sequence node is basically the opposite. It's going to go from left to right, but it's going to do them in sequence. If this succeeds, instead of stopping, it's going to play the next one. If it succeeds, it's going to go to the next one. And it's only going to stop if one of them fails. Our last one is our simple parallel. Basically, this is a way to run one thing all the time. One thing basically all the time in parallel with another group of things. So for our example here, we could be playing a sound while at the same time we're doing another selector that moves directly towards an object and then waits. These will all be covered in more detail in their individual videos with another group of things. So for our example here, we could be this is going to stop if one of them fails. Our last one is our simple parallel. Basically, this is a way to run one thing all the time. One thing basically all the time in parallel with another group of things. So for our example here, we could be playing a sound while at the same time we're doing another selector that moves directly toward an object and then waits. These will all be covered in more detail in their individual videos. So, in this instance here, we have our decorator. Now our decorator is designed basically to check and see if we should be doing something. It's a condition. In this case, is our player alive set? Have I set our player alive variable, which is here, to true or false? Is it currently set? If it is, then it's going to go ahead and it's going to allow all of this to run. If it's not, it's going to fail. Now, since we don't have anything else to do in here, nothing's going to happen. So if our player's not alive, nothing's going to happen. Our next one under this is our service. Our service is basically, you can think of it as a function that reoccurs every interval, and our interval is settable over here. Basically, all I'm doing here, and this is a normal event graph, is every time it ticks, I'm checking to see if our player is alive, and if so, setting the variable. And if the player is alive, I'm setting a valid location for that player. So, if we have a valid player, it's going to go ahead and run this. Now this will run as long as we are here. So let me go ahead and just hit our play button and go back to here, and you're going to see how this works. So right now we are running this node. This node is not failing. It is successful because we do have a player that's alive. And this right here, every 0.4 to 0.6 seconds, is checking to make sure the player is still alive. And if it is, it's setting a valid location for the player. Now you'll notice down here, we have our stuff executing. Basically, I'm telling it to move to our player, the location I've set here. Once it successfully gets there, it's going to go ahead and wait 1 second. Now, you're watching these bounce back and forth because every half a second, I'm basically nulling out the player, which means this is going to fail. Right here, I'll move to because it can't fail. And then the next ticket's going to set it as valid. This entire condition here, our selector and our tasks, are running all the time as long as we're in our composite node here. This right here only runs if this node is active and only runs when we tell it. So it's like something that's happening at the same time. So to show our example, let me go ahead and run this and you're going to see what's happened. Basically, we have our little character there and he's going to move over to my guy. Now, every half a second, I'm running my service, which is updating my location. So if I move, our character doesn't follow immediately. And if you notice, he's not coming towards me. He's basically going to the last known location every time that service is ran. Now, this looks a little silly and stilted, but if you notice, I actually have basic working AI using my behavior tree. And if I was to fall off, unfortunately, he is going to follow me as far as he can. And I have kill Z shut off, so that really doesn't help. So let's turn kill Z to a more valid value, something like that, and try that again. Now if we were to actually fall off, you'll notice he's stuck. He's done. And if we were to go to our behavior tree, you're going to notice it's failing. This is running. Our player live is not set. You'll notice he's... Try that again. Now if we were to actually fall off, you'll notice he's stuck. He's done. And if we were to go to our behavior tree, you're going to notice it's failing. This is running. Our player live is not set, and because it's not set, it's basically going to abort, and we're just going to keep failing out. Now, in a traditional, less example tutorial version of this, you'd actually have a different selector above this that's actually going to tell the AI what to do. And you're going to have the AI maybe do nothing, and then check and see if the player's alive. And if the player's alive, then do a move task. Or maybe look for a new player if there's no player live. Or maybe every 6 seconds try to find the closest player, so that way it updates the player. That's what the behavior trees are for. You can have it do all those different things, running different services, and basically you run it from left to right, top to bottom, for programming your artificial intelligence. So this is a quick overview of what a behavior tree is. Like I said a few times at this point, every decorator node, every service node, every task node, and all of our different composite nodes will be covered separately in individual videos, and then it will all be brought together in another video or 2 or 3, however much is needed, to cover it more in depth, actual working AI from start to finish, cascading sequences of nodes, and basically creating a more advanced AI using everything we've learned. So, if you have any questions or comments, please... Tree composite nodes. This is going to be a very short video. The composite nodes themselves are covered in more detail individually. This is just an overview of what is considered a composite node. So a composite node, you can right-click anywhere in your graph, and you'll see you have selector, sequence, and simple parallel. Let's go ahead and pull up each of these. And you'll notice for the most part they are fairly similar. Now the composite nodes are going to be our nodes that are gray in nature. They're going to have our lines for connecting at the top, and then one of the things that if you're used to using normal nodes you might find annoying, in order to move these you're going to have to select them on the sides to move. If you try to drag from the top, of course, it's not going to work. Now each of these has an individual use and individual quirkiness and parameters that can be set. Those are covered in the individual videos. But for the most part you can think of a composite node as the root of a branch of the tree for your behavior tree. They can have decorators applied to them, they can have sequences and services that are ran on them, and they can fire off tasks or other composite nodes to fire off more roots of branches, so that way they could fire off all more tasks, etc., etc. They can go as deep as you want. So, just to summarize it, composite nodes, they're the basic building block of your branches for your behavior tree. If you have any questions or comments, please feel free to leave them below. Also, please see the individual videos for each of the composite nodes.
Ist man feiern?
Bum 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 bum. The video 4, example here, we're going to cover AI behavior tree selector node. I have an example here. We're going to cover the selector node and basically how it works and what it's intended to be used for. So a selector node is one of our basic composite nodes. The intention of it is basically to do something based on a decorator task or a service that you have running on it, and then run the tasks underneath it from left to right, and it will only run the one that succeeds. So it will start with this one, and if it succeeds, nothing else is going to happen. But if it fails, it's going to go and run the next one. It is selecting a valid task. Now, if all of them fail, then the selector node itself will fail. If one of them succeeds, then the selector node itself succeeds. Now you may be asking, well, why does that really matter? Keep in mind, a selector node can be connected to another selector node. So if we did something like this, and then we hooked up here, and then we did another selector node here, this would matter in terms of failing and succeeding. This selector node is going to fire, which means it's going to go from left to right and fire these ones. And if one of these fails, it's going to fire this. If one of them succeeds, it's never going to fire the one on the right. Remember, the selector node only cares about if something succeeds, and it will never fire anything else after that. So let's see this in an example. Let me hook this up, and let me go ahead and run this. Now if I run this, and I go back to here, we're going to see the selector node firing, and it's firing off a wait task of 5 seconds. Now, if you watch every 5 seconds, it's going to quickly flash, as once this finishes, it reruns from the root, refires the selector node, and then reruns the wait node. Now, of course, we're never going to see the move to work because this one's always going to succeed. If we were to reorganize and hit save, you're going to notice our indexes, which is a 1 and a 0, are going to change. Now it's going to fire the left node first, which is our move to, and then the wait node second, assuming the move to fails. If we run this again, then we hit play, go back into here, you're going to notice our wait node is firing, and this one is not. You'll also notice every 5 seconds, it's going to try to do the move to again, and it's going to fail and fire off the wait node. My move to currently for this example is set to find the Blackboard key player location and move to it. Now, since I'm never actually setting it, it's going to fail every time for our example. Now, our selector node itself usually has decorators and services attached to it that allow you to determine what it's going to do. Decorators and services are handled in other videos, but let me just show you how this would work properly using a proper service. So in this case, we have our service, which is going to set our player location every half a second. Now if we run this, and then we go back to our behavior tree, we're going to notice, well, it's still failing. Well, it failed because our initial move to location wasn't set the first time we came through, which means it ran our wait 5 seconds. After half a second, this service was ran. It went ahead and set our player location, which means the next time we came through, if we look over here, we find our players now sitting next to us, our AI, because the move to was successful. If I was to take and move our little guy over, we're going to find him followed to the location, like we expect. And if we check out our behavior tree, we're going to see it's working like it's supposed to. It fires the move to. Once the move to is successful, it's going to go ahead and fire the wait if this fails. If not, it's going to keep doing the move to. And with the way this is set up, it's designed to fail every half a second, so that way this will get fired. So that is what the selector node is used for. If you want something to happen, it doesn't necessarily mean everything has to happen. You want something to happen. Maybe you want to check to see if there's a player. Well, that would be a service. Let's say you want to do something like this. You want it to move to a location. And if there's no valid location, you want it to wait until it can do it again. But you want it to do something. You don't want it to just sit here and hammer. Like, for example, if we moved our wait node and unhooked it, and then we went ahead and set our move to location to fail, and we ran this, what you're going to see is it's going to run constantly. Blackboard root runs the selector, and if you notice it's flashing, it's because it's constantly, every tick, trying to move to an invalid location, which we don't want. We want, if this fails, for it to do something else. That's why we have the selector node, so when we actually run it this time, it's not going to continually hammer our AI every tick to try to do something. It's going to say, hey, you know what, we screwed up, let's wait 5 seconds and try again. And then, hopefully, the player location will actually work properly, and boom, we're good to go. So, that's what our selector is for. It's a left to right. If something succeeds, it never continues. If something fails, it continues. If you have any questions or comments on a selector node, please feel... So, that's what our selector is for. It's a left to right. If something succeeds, it never continues. If something fails, it continues. If you have any questions or comments on a selector node, please feel free to leave them below.
Need a 3D animation for your product? It's
Bum 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 bum. Or, what is AI? The behavior tree sequence node. Go ahead and delete this. So let's go ahead and cover what this is. The sequence node, let me go ahead and delete this for now, is right here, and this is one of our basic composite nodes. The intention of it is to be the root of our behavior tree branches, and to allow us to determine what we're going to do based on services that may run or decorators that may run and things like that. Now, the biggest difference is our sequence node is basically the opposite of our selector node. The sequence node will execute from left to right, but will only stop executing if one of the children fails. The selector node is the opposite, whereas when one of the children fails, it continues on to the next one. The sequence node is intended to run in sequence until something fails. And it seems pretty simple, but let's see how it works in theory. Well, in practice, we'll see how it works. So let's hook up our Blackboard here. We're going to go ahead and run this, and we're going to see how it works. If we go back to here, basically it's firing off our sequence node. The first task on our sequence node on the left is our wait. It's going to go ahead and wait 5 seconds. Then it's going to fire off our move to the player location. Since our move to the player location is failing, it's going to go ahead and rerun everything and go back to our wait node. Now, in order to make it work, I need to put in my service here. Services are covered in another video. And what this is going to do is let me figure out where my player's at, assign it to the player location Blackboard value, and then move my character to that location. So now let's go and run this, and we're going to see something different. We're going to see it wait for 5 seconds, and then since this succeeds, it does the move to. Now the move to is going to go ahead and run. Once it succeeds, it's going to fire back over here. The whole thing's going to fire again. We'll wait for 5 seconds, and then we'll run the move to again. So let's go back to our screen here, and we'll see it in action. After the 5 seconds, our character is going to get our new location and move to us. Once it gets there, it's going to wait 5 more seconds. The character is going to find our new location, and then it's going to move to us. And it's going to continue like that until everything blows up, in theory. So that's what our sequence node is for. It's intended to fire from left to right based on the sequence you order them in, which if you notice here, let me overdrive this and zoom in. Hold on. You'll notice we have 0 for our first node and 1 for our second node for the sequence. If we were to add another one in here, let's add another wait node just because we can. They're easy. You're going to notice we now have it reordered. 0, 1, 2. Now, if you were to reorder these, you'll notice they are not going to change immediately. In this instance, we have a 2, 1, 0. If we were to save it, it's going to go ahead and run the behavior tree again and reorder our nodes appropriately. So, there you go. That is what our sequence node is for. It's intended to start off the base of the branch, do our decorators or services as needed, and then fire off the tasks from left to right and continue firing from left to right as long as the tasks succeed. Once they fail, it immediately aborts our sequence node and starts over from above it. If you have any questions or comments, please feel free to leave them below. Hello. Simple Parallel. Go ahead and cover how this works. So this is our Simple Parallel node. You can access it from Composites Simple Parallel, and you're going to find it basically has one input and two outputs. Now you can go ahead and you can add in your normal things like a decorator and a surface, but the intention of the Simple Parallel node is basically to allow a single main task to be executed alongside with a full tree underneath it. Now, behavior trees are intended to be event-driven, so the Simple Parallel node isn't something you're going to use most of the time. You'll use the selector or the sequence node. But the Simple Parallel node could have some uses, maybe if you want to have something playing or doing or a simple task running while you're also checking maybe for another target, or maybe you want something to run no matter what, and then you have something else running while it can. So let's just go ahead and cover how this works. We have our Simple Parallel node, and if you notice, unlike our other composite nodes, it has two outputs. The left one is purple colored because it is a task output. It will only run a task. So in this case, I have the wait node hooked up with a 2-second wait time. Now on the right side, we have our normal output. We can hook up other composites and we can hook up tasks directly. So for this example, what I've done is I've told it, let's run the task for 2 seconds. We're going to wait. Now at the same time, we're going to run this set of nodes, which is a selector, which is going to check and see if our player is alive, and if it is, set our player's location to one of the Blackboard variables, and then move to that player's location. Now let's watch these run in the behavior tree itself, and then we'll watch it in the map, and I'll show you how they're working. So if I go ahead and run this and go back to here, you're going to see it running like this. You can see both nodes running at the same time, and you're going to see no real difference from our normal selector sequence nodes. And that's because what I've done is the composite node Simple Parallel is the only one that actually has some parameters, and the parameter it has is the finish mode. By default, it's set to immediate. Now you notice when we ran it before, it didn't look like there was anything odd happening. Now if we run it this time, what you're going to see after 2 seconds is the entire thing is going to abort and it's going to start over again. So let's go ahead and check that out. So you're going to see every 2 seconds this sequence over here flashing, because every 2 seconds the entire thing is starting over. We run our task right here, we wait 2 seconds. When this finishes, it goes ahead and immediately finishes everything else on the right hand side, says this is completed successfully, and then of course it's going to go back up our tree to either another node above it or a root in this case. So if we actually see this in motion, watch what happens to our character. Rather than our character moving using the simple move to our player's location, it's going to start hitching. So if you watch, it's going to move, stop, move, and then it gets to our location. What's happening is our behavior tree is running, and after 2 seconds, it's aborting our move to location. Our root is refiring, doing the wait for 2 seconds, and then in parallel, telling it to move again. So basically, we're forcing this over here to restart based on this completing successfully. And of course, if we don't want that, you can change this to delayed, and if we run this and watch it, you're actually going to see it work what it looks like normal. It's going to move smoothly to our move location. And we go back over here, and it's going to continue working like we expect it to. What's happening in that case is actually successfully. And of course, we is refiring, doing the wait for 2 seconds, and then ending. So if you watch, it's going to move, stop, move, and then it gets to our location. What's happening is our behavior tree is running, and after 2 seconds, it's aborting our move to location. Our root is refiring, doing the wait for 2 seconds, and then in parallel, telling it to move again. So basically, we're forcing this over here to restart based on this completing successfully. And of course, if we don't want that, you can change this to delayed, and if we run this and watch it, you're actually going to see it work what it looks like normal. It's going to move smoothly to our move location. If we go back over here, and it's going to continue working like we expect it to. What's happening in that case is our wait node is firing, but when it finishes after 2 seconds, it's telling it to go ahead and wait. Let's wait for your actual tree over here to finish before we consider this successful. So that is what our Simple Parallel node is for. Like I said, it's not usually used very often. It has some uses if you want to run things in parallel. Keep in mind, you're only going to run a task in parallel with another set of composite nodes, or another task. For the most part, since behavior trees are event-driven, using the selectors and sequences to determine what you want to do and then do it, and then using things like decorators and services to adjust those things in real time, gives you a much more modular feel rather than just simply running something in parallel until it does or does not work. So that's it. That is what our Simple Parallel composite node is. If you have any questions or comments, please feel free to leave them below.
Tomatoes?
Hello, welcome to the video for what is AI? The behavior tree decorator nodes. Creator node is, but we're not going to go into specific detail about each of the decorator nodes. Each of the decorator nodes will have their own video with an example showing how they're used. So let's go ahead and get started. So, the decorator node is basically a conditional node. It's intended to allow you to determine if you should or should not do something. Basically, you can kind of think of it as an if node. If it is successful, then it's going to continue on with the composite node, which is our sequence or our selector, and then allow a task to run. So let's go ahead and look at one of these and check out the basics. So you can access the decorator nodes, the pre-built ones, by right-clicking on something that can accept a decorator node. Now if you notice when I right-click anywhere in here, we don't see decorator nodes anywhere. Well, decorator nodes, because like I said, they're basically an if, they determine if something can be done, they must be attached to something. They may be attached to a composite node, or they may be attached to a task itself. Now, the decorator nodes are these blue nodes here. As you can see, I have 4 of them currently here. Now, you can choose to not use decorator nodes. In this case, I'm simply using a service attached to a selector, so that way this service is always running. Underneath that, I have decorator nodes that determine whether or not I should do something. And you can stack more than one decorator node. For example, I could add another decorator here for Blackboard, and now I'd have a cooldown and a Blackboard-based condition for decorators. Now, when you have multiple decorators, it is going to go from top to bottom, vertically, and if one fails, then everything below it is going to fail as well. You can reorganize them simply by dragging and dropping, as you can see here. And there we go. So, the basics of the decorator nodes. Now, if you notice, I have 3 technically different nodes here. A decorator example, Blackboard-based condition, and a cooldown. All of them will have different details that determine how the decorator fires. So in this example, for this one, we have a flow control section, a Blackboard section, and then the description section. And the description section just allows you to change the name. So from like Blackboard-based condition to, is the player valid? And now it's is the player valid. So that's what the node name is for. Now, the things that are pretty much common that I'm going to try to cover in this video is the way flow works with decorators in terms of observing and aborting, as well as accessing the Blackboard. The section you'll probably find common between some of the nodes is going to be our Blackboard section. The Blackboard section, for example in this one, is where you would set up what key in our Blackboard, right now here's our key for player, what key we're actually going to do something with. In this case, I only have player, so it's the only option, but if I have more than one, that is how you would set what we're doing with it. Now, specific things like for our Blackboard decorator node here are things like our notify observer, observer aborts, the key query, the Blackboard key. I'm not going to go into details because that will be covered in the actual Blackboard decorator node itself, but one thing that is important between all of our decorators is understanding how the flow works, which is right here where our observer aborts section is. Some of them may have 4 settings in here, none, self, lower priority, and both, and some of them may only have something such as none, lower priority, and then this one, for example, has none and self. So it's important to understanding how these work. So let's go ahead and look at how this one works in terms of the flow, and we'll see how it's broken, and I'll explain the different flows.
Tomato?
Remember the selector setup? So if I run this, and I go back to here, we're going to see it flowing like this. Now when this one fails, what's going to happen is it's going to go backwards up the chain, and then it's going to try to go down because I'm using a selector. Remember the selector setup where if the left one fails, it'll then try the right one. Now with the way I've designed this behavior tree, it's going to fail no matter what. It's going to get stuck at the top and nothing's going to happen, because my decorators are failing and not allowing the task to run. So in this instance, I have a decorator here asking, is the player valid? Is my player set? And if we look in the bottom right, we have our player key, and it's currently set to none. Because it's set to none, up here under observer aborts, I have it set to none. That means it's going to abort nothing that is going on. Now you ask yourselves, well, it failed, so what does that mean? How is that true? What is going on here? Because it's set to none, up here under observer aborts, I have it set to none. That means it's going to abort nothing that is going on. Now you ask yourselves, well, it failed, so what does that mean? How is that true? What is going on here? Well, let me get rid of this decorator example and show just a plain, simple sequence along the left and right. I'm going to change my wait here to something ridiculous, like 50 seconds. So in theory, how this works is it's going to go down, this is going to set the player, this is going to see if the player is currently set, and if so, it's going to wait 50 seconds. Now, because I have observe aborts none here, what you're going to see happen is this is going to sit here, and it's going to start waiting for 50 seconds. Down here we see our player, and our player is now currently none. Well, this one is checking for the player, and the player has changed. Why are we still waiting? Why are we still down here? Well, this is going to continue running for our 50 seconds. Once the 50 seconds is up, it's going to go back up here and finish successfully. Then it's going to go back up here, and this is going to continue running. Now, the next time this runs through here, the sequence node is going to check this. This is going to be invalid the next time we run, because our player is now set to none, and it's going to abort, and it's going to fail here, and it's going to try this side. So, what if we want when the player is no longer valid? Because that's the whole point of this. If the player is no longer valid, we don't want to do anything. What if we wanted this to stop? Well, that's what our aborting is for. So, if we have it set to abort self, you're going to notice one thing immediately. We have a little note here that says node aborts self, and you're going to see this color coding based on this. None, nothing's going to happen. Self, everything that's color coded is going to abort when this decorator fires. So let's go ahead and run this again. And this time you should see when our condition is met, which is going to be after approximately 5 seconds, this is going to change to none. Now you notice this is no longer waiting. You'll notice a red thing here because it failed. And it's going to travel back up, and it's going to continue trying to do what it can. Now in this case, because I'm using a selector node, this left chain fails, so it's going to try the right chain. Now my right chain has another condition in here, checking if the player's set. It's failing, so it fails back up, and now nothing can run, and we're basically stuck. Our player AI can't do anything. That's kind of what we wanted there. So that is what the observer aborts self does. It's going to abort itself and anything below it. Now the next option is lower priority, and you're going to notice an immediate change. We now have this in a blue, well, a darker blue. This is no longer colored, and you're now going to notice this is colored by our darker blue. Lower priority means basically anything to the right, because remember we go from left to right when we execute. Higher priority, lower priority, and if I had more, even lower priority. So actually let's show that in use. I hate moving these things. We'll add a selector node here, and then we'll go ahead and check this, and you'll notice now the selector node is dark blue because it would abort as well. So in this case, if you had multiple things running along your chain, along your behavior tree, let's say you had this branch here running and this branch here running. So let's say you had everything that was highlighted running. When this aborts in this case, let's just go ahead and run this. We're going to see everything that was highlighted and in that abort sequence abort. Now, if you notice here, it's now set to none, but this is still running. Well, again, it's set to lower priority. When we see the highlight here, these are the only ones that are going to abort. This is not selected, it's not going to stop. It's only going to stop everything else. In order to stop everything, we have the both. Now, if you notice, we have nodes aborted by mode self and lower priority, and now everything is going to stop when this fails. If we run it again to show you, you're now going to see after 5 seconds, this node will fail, it's going to abort this, and it's going to abort everything else. So there you go. That's what our observer abort section is for. Now, that is something that is going to be common for all of your decorators if it uses the observer and the observer aborts. So that's something to keep in mind. That's why it's covered in the decorator video itself. None means nothing's going to happen when it fails. It will eventually stop it from working once your tasks means nothing's going to happen when it fails. It will eventually stop it from working once your tasks or any conditions under it are met, but nothing will immediately happen. Self, just itself, and anything below it will stop. Lower priority, anything to the right. Self, just itself, and anything below it will stop. Lower priority, anything to the right of it on that same composite node is going to fail. Both means both itself and lower priority are going to fail. Okay, so what else do we have here? The Blackboard key I've mentioned is references to your Blackboard key, and then other things are going to be individualized, which will be covered in their videos. Cooldown has this cooldown section. Blackboard-based condition has this notify observer section, which will be covered. One thing that I haven't covered is not only can you use the built-in decorators, you can create your own decorator itself up here in the new decorator section. When you do that, it's going to ask you which parent base class you want to use. In this case, you're probably going to use the decorator blueprint base. I've gone ahead and actually created an example for this. So let me figure out where I put it. This is a decorator. Okay, what did I call it? I called it BT decorator example. So let's find BT decorator example. So here's our custom decorator. This is a decorator I made. And if we look at it, it's pretty much duplicating what our existing Blackboard decorator does. Let me go ahead and put it in here. Let's add a decorator, and we'll set this to our decorator example. Now, how I've set this decorator example up is it works just like any other event graph. You have something that's going to happen, and then set this decorator example up is it works just like any other event graph. You have something that's going to happen, and then something's going to be returned. All of the functions you can use can be overridden right here. You have your tick, if the observer was deactivated, if the observer was activated, when execution starts on this node, when execution finishes on this node. And execution is when it runs through here. Observing is, in this case, for example, when we set up an observer, and that is always constantly checked. So, for example, it's basically an event dispatcher. It's a callback, it's a notification. You're observing something, it's whether it deactivates or activates it, and then whether or not this node gets executed on the start, basically begin play, or finish, which is end play. And the last one is this perform condition check, which is handy. This basically allows you to do something and return back a true or false value. So in this example, basically, I have an actor to check Blackboard key. That means I'm going to have a Blackboard key here I'm going to set up that I want to assign to this variable called actor to check. So I'm checking that value. I'm getting that Blackboard value as an actor, because what I want to do is compare that actor to nothing. I want to see if that actor is not equal to nothing, if it's not null, if it's a valid actor. And then I'm returning the result. So now when I go back to our behavior tree, and I was to pull up this example, by default you're going to find it set to nothing. I change this to my player, because that's my player Blackboard value. And then basically I tell it if I want to abort itself or none. So I'm going to set it to abort self. So in this case here, even though we have this set up here and it's going to abort everything below it, let's go ahead and remove this. And let's say we want it just on the task itself, and we don't actually want it on the sequence node. Now if we run this, we should see a very similar result to before. I basically recreated this Blackboard check, but in this case I did it using my own settings or any of my own checks. So as you saw in here, after the time, it went to none. My check inside of here is basically checking to see if the actor is equal to not equal, equal to nothing, and then it returns the value of true or false. In here I have it set to abort itself if that condition is true. And then you have an inverse condition in here as well. So for example, if I check this and I ran it, it's going to pretty much fail immediately, because this is going to start off as false because I didn't have that check in place. So that's how you can use a custom decorator. And of course, there's many other things you can do with a custom decorator. You could have it do a line of sight check, for example, or maybe a distance check. Maybe you have a move to node or move to sequence, and after your player, every time your player moves, maybe you want to make sure it aborts within a certain distance. Maybe you want to make sure you can always see your player. Maybe you have to do a line of sight check every certain amount of time. And your service here says, your service runs every half a second. Your service is going to run 2 checks. It's going to assign a player that it can see, and then it's going to assign a line of sight, whether your AI can see your player. And down here in your move to task, you're going to have a line of sight check decorator. And if it's true, it's going to continue moving. And if it's false, it's going to stop moving. So you can have it where it works like that, where as soon as your player gets out of line of sight and it reruns the service, it updates that Blackboard variable. Your custom node says, oh, well, okay, they're out of line of sight. Let's go ahead and stop that. And then you can have it abort the move to task. There are plenty of obvious uses to it, but that's a quick example of a decorator that you can create yourself. So that's going to cover it up for the most part. Like I said, there are individual videos covering each decorator node that comes with the system built in. As you can see, there's a list of them. You can create your own custom decorator. And remember, decorators are basically, you can think of them as basic if statements. They are conditionals. The intention is to allow the things below it to happen if these settings are valid. That's it. If you have any questions or comments, please feel free to leave them below.
Das größte Missverständnis bei fast allen, die programmieren lernen, ist die Idee.
Welcome to the video for What is AI? And go into specific detail about each of the decorator nodes, So, the decorator node is basically a conditional node. It's intended to allow you to determine if you should or should not do something. Basically, you can kind of think of it as an if node. If it is successful, then it's going to continue on with the composite node, which is our sequence or our selector, and then allow a task to run. So let's go ahead and look at one of these and check out the basics. So you can access the decorator nodes, the pre-built ones, by right-clicking on something that can accept a decorator node. Now if you notice when I right-click anywhere in here, we don't see decorator nodes anywhere. Well, decorator nodes, they may be attached to a composite node, or they may be attached to a task itself. Now, the decorator nodes are these blue nodes here. As you can see, I have 4 of them currently here. Now you can choose to not use decorator nodes. In this case, I'm simply using a service attached to a selector, so that way this service is always running. Underneath that, I have decorator nodes that determine whether or not I should do something. And you can stack more than one decorator node. For example, I could add another decorator here for Blackboard, and now I'd have a cooldown and a Blackboard-based condition for decorators. Now when you have multiple decorators, it is going to go from top to bottom, vertically, and if one fails, then everything below it is going to fail as well. You can reorganize them simply by dragging and dropping, as you can see here. And there we go. So, the basics of the decorator nodes. Now if you notice, I have 5 different, well, I have 3 technically different nodes here. A decorator example, Blackboard-based condition, and a cooldown. All of them will have different details that determine how the decorator fires. So for in this example, for this one, we have a flow control section, a Blackboard section, and then the description section. And the description section just allows you to change the name. So from like Blackboard-based condition to, you know, is the player valid? And now it's is the player valid. So that's what the node name is for. Now the things that are pretty much common that I'm going to try to cover in this video is the way flow works with decorators in terms of observing and aborting, as well as accessing the Blackboard. The section you'll probably find common between some of the nodes is going to be our Blackboard section. The Blackboard section, for example in this one, is where you would set up what key in our Blackboard, right now here's our key for player, what key we're actually going to do something with. In this case I only have player, so it's the only option, but if I have more than one, that is how you would set what we're doing with it. Now, specific things like for our Blackboard decorator node here are things like our notify observer, observer aborts, the key query, the Blackboard key. I'm not going to go into details because that will be covered in the actual Blackboard decorator node itself, but one thing that is important between all of our decorators is understanding how the flow works, which is right here where our observer aborts section is. Some of them may have 4 settings in here, none, self, lower priority, and both, and some of them may only have something such as none, lower priority, and then this one, for example, has none and self. So it's important to understanding how these work. So let's go ahead and look at how this one works in terms of the flow, and we'll see how it's broken, and I'll explain the different flows. So if I run this, and I go back to here, we're going to see it flowing like this. Now when this one fails, what's going to happen is it's going to go backwards up the chain, and then it's going to try to go down because I'm using a selector. Remember the selector is set up where if the left one fails, it'll then try the right one. Now with the way I've designed this behavior tree, it's going to fail no matter what. It's going to get stuck at the top and nothing's going to happen, because my decorators are failing and not allowing the task to run. So in this instance, I have a decorator here asking, is the player valid? Is my player set? And if we look in the bottom right, we have our player key, and it's currently set to none. Because it's set to none, up here under observer aborts, I have it set to none. That means it's going to abort nothing that is going on. Now you ask yourselves, well, it failed, so what does that mean? How is that true? What is going on here? Well, let me get rid of this decorator example and show just a plain, simple sequence along the left and right. I'm going to change my wait here to something ridiculous, like 50 seconds. So in theory, how this works is it's going to go down, this is going to set the player, this is going to see if the player is currently set, and if so, it's going to wait 50 seconds. Now, because I have observe aborts none here, what you're going to see happen is this is going to sit here, and it's going to start waiting for 50 seconds. Down here we see our player, and our player is now currently none. Well, this one is checking for the player, and the player has changed. Why are we still waiting? Why are we still down here? Well, this is going to continue running for our 50 seconds. Once the 50 seconds is up, it's going to go back up here and finish successfully. Then it's going to go back up here, and this is going to continue running. Now, the next time this runs through here, this sequence node is going to check this. This is going to be invalid the next time we run, because our player is now set to none, and it's going to abort, and it's going to fail here, and it's going to try this side. So what if we want when the player is no longer valid? Because that's the whole point of this. If the player is no longer valid, we don't want to do anything. What if we wanted this to stop? Well, that's what our aborting is for. So if we have it set to abort self, you're going to notice one thing immediately. We have a little note here that says node aborts self, and you're going to see this color coding based on this. None, nothing's going to happen. Self, everything that's color-coded is going to abort when this decorator fires. So let's go ahead and run this again. And this time you should see when our condition is met, which is going to be after approximately 5 seconds, this is going to change to none. Now you notice this is no longer waiting. You'll notice a red thing here because it failed. And it's going to travel back up and it's going to continue trying to do what it can. Now in this case, because I'm using the selector node, this left chain fails, so it's going to try the right chain. Now my right chain has another condition in here, checking if the player set. It's failing, so it fails back up. And now nothing can run, and we're basically stuck. Our player AI can't do anything. And that's kind of what we wanted there. So that is what the observer abort's self does. It's going to abort itself and anything below it. Now the next option is lower priority, and you're going to notice an immediate change. We now have this in a blue, well, a darker blue. This is no longer colored, and you're now going to notice this is colored by our darker blue. Lower priority means basically anything to the right, because remember we go from left to right when we execute. Higher priority, lower priority, and if I had more, even lower priority. So actually let's show that in use. I hate moving these things. We'll add a selector node here, and then we'll go ahead and check this, and you'll notice now the selector node is dark blue because it would abort as well. So in this case, if you had multiple things running along your chain, along your behavior tree, let's say you had this branch here running and this branch here running. So let's say you had everything that was highlighted running. When this aborts in this case, this is go ahead and run this. We're going to see everything that was highlighted and in that abort sequence abort. Now, if you notice here, it's now set to none, but this is still running. Well, again, it's set to lower priority. When we see the highlight here, these are the only ones that are going to abort. This is not selected. It's not going to stop. It's only going to stop everything else. In order to stop everything, we have the both. Now, if you notice, we have nodes aborted by mode self and lower priority, and now everything is going to stop when this fails. If we run it again to show you, you're now going to see after 5 seconds, this node will fail, it's going to abort this, and it's going to abort everything else. So there you go. That's what our observer abort section is for. Now, that is something that is going to be common for all of your decorators, if it uses the observer and the observer aborts. So that's something to keep in mind. That's why it's covered in the decorator video itself. None means nothing's going to happen when it fails. It will eventually stop it from working once your tasks or any conditions under it are met, but nothing will immediately happen. Self, just itself, and anything below it will stop. Lower priority, anything to the right of it on that same composite node is going to fail. Both means both itself and lower priority are going to fail. Okay, so what else do we have here? The Blackboard key I've mentioned is references to your Blackboard key, and then other things are going to be individualized, which will be covered in their videos. Cooldown has this cooldown section. Blackboard-based condition has this notify observer section, which will be covered. One thing that I haven't covered is not only can you use the built-in decorators, you can create your own decorator itself up here in the new decorator section. When you do that, it's going to ask you which parent base class you want to use. In this case, so decorator Blackboard. And if we look at it, it's pretty much duplicating what our existing Blackboard decorator does. Let me go ahead and put it in here. Let's add a decorator, and we'll set this to our decorator example. Now, how I've set this decorator example up is it works just like any other event graph. You have something that's going to happen, and then something's going to be returned. All of the functions you can use can be overridden right here. You have your tick, if the observer was deactivated, if the observer was activated, when execution starts on this node, when execution finishes on this node. And execution is when it runs through here. Observing is, in this case, for example, when we set up an observer, and that is always constantly checked. So for example, it's basically an event dispatcher. It's a callback, it's a notification. You're observing something, it's whether it deactivates or activates it. And then whether or not this node gets executed on the start, basically begin play, or finish, which is end play. And the last one is this perform condition check, which is handy. This basically allows you to do something and return back a true or false value. So in this example, basically, I have an actor to check Blackboard key. The stored value as an actor, because what I want to do is compare that actor to nothing. I want to see if that actor is not equal to nothing, if it's not null, if it's a valid actor. And then I'm returning the result. So now when I go back to our behavior tree, and I was to pull up this example, by default you're going to find it set to nothing. I change this to my player, because that's my player Blackboard value. And then basically I tell it if I want to abort itself or none. So I'm going to go ahead and set it to abort self. So in this case here, even though we have this set up here and it's going to abort everything below it, let's go ahead and remove this. And let's say we want it just on the task itself, and we don't actually want it on the sequence node. Now if we run this, we should see a very similar result to before. I basically recreated this Blackboard check, but in this case I did it using my own settings or any of my own checks. So as you saw in here, after the time, it went to none. My check inside of here is basically checking to see if the actor is equal or not equal. Equal to nothing, and then it returns the value of true or false. In here I have it set to abort itself if that condition is true. And then you have an inverse condition in here as well. So for example, if I check this and I ran it, it's going to pretty much fail immediately, because this is going to start off as false because I didn't have that check in place. So that's how you can use a custom decorator. And of course, there's many other things you can do with a custom decorator. You could have it do a line of sight check, for example, or maybe a distance check. Maybe you have a move to node or move to sequence, and after your player, every time your player moves, maybe you want to make sure it aborts within a certain distance. Maybe you want to make sure you can always see your player. Maybe you have to do a line of sight check every certain amount of time. And your service here says, you know, your service runs every half a second. Your service is going to run 2 checks. It's going to assign a player that it can see, and then it's going to assign a line of sight, whether your AI can see your player. And down here in your move to task, you're going to have a line of sight check decorator. And if it's true, it's going to continue moving. And if it's false, it's going to stop moving. So you can have it where it works like that, where as soon as your player gets out of line of sight and it reruns the service, it updates that Blackboard variable. Your custom node says, oh, well, okay, they're out of line of sight. Let's go ahead and stop that. And then you can have it abort the move to task. There are plenty of obvious uses to it, but that's a quick example of a decorator that you can create yourself. So that's going to cover it up for the most part. Like I said, there are individual videos covering each decorator node that comes with the system built in. As you can see, there's a list of them. You can create your own custom statements. They are conditionals. The intention is to allow the things below it. Have any questions or comments?
Das größte Missverständnis bei fast allen, die programmieren lernen.
The video 4. What is AI behavior tree decorator, the compare Blackboard entries node? I have fired up a quick little example here. We're going to cover the node and see how it works. So here's our Blackboard entries node. It is a decorator, so you can add it either to a task or a composite. And it's simple, add decorator, compare BB entries. So by default, we're going to come up with these for our settings. You're going to abort nothing, and you have no values for your key. Now, like all the other Blackboard nodes, when you first pull them up, it's going to default their Blackboard entries to whatever your first key is going to be for a valid entry. So make sure you change these to whatever you actually want to observe. So for example, what we're going to do is we're going to see if the player is equal to the... We have a player object key and an AI enemy key. Using this service here, I'm going to alternate between what the values are, and we're going to use the compare Blackboard entry node to compare them, and then do something. So let's set our player for our first key and AI enemy as our second key. And this is a pretty simple equal to or not equal to node. By default, it's set to equal to, but of course you can change it to is not equal to. We're going to set our observer up to abort nothing because that's our default. Let's go and run through our example and watch our node values. When we start, our player is set to generic character, and our AI enemy was set to none. Then the player changes to none after 5 seconds, and then our AI enemy, after another 5 seconds, or 10 seconds total, will change to the AI character's value. So our compare Blackboard entry will compare and only allow the sequence to run if our values are equal. Let's set this to abort self so we can actually watch it in real time. So when we run this, what you're going to see is me not hitting the play button. We're going to see in the beginning, it ran very quickly because our values were both set to none. Then it stopped because our player was set to the player. Now that they're both back to none, it was running. And now that it's back to AI enemy, it's set to fail again. So let's go ahead and watch that again so you can watch it happen. Assuming I can hit the stop key. We have the same value as none, it ran. We have different values, it stopped running. We have the same values again as none. And then we have the different values again as none and generic AI character. And if course we were to flip this and say is not equal to, we're going to get the opposite result. We're going to watch it succeed because the values don't match, fail because the values match, and then succeed again when the values don't match. So it's pretty simple. It's a simple equal or not equal node. Make sure you have two valid values. Keep in mind this is going to be an exact comparison. You're not going to be able to, for example, I have a bool value here, and I set this to is player equal to true bool, and I run it. Actually, we'd want, yep, is equal to, okay. And run it. It's going to fail because true bool is a Boolean value, and its value is different than whatever's held currently in my player and my enemy. So keep that in mind. Now, if you wanted to use, if I can go back to it, this to compare if two things are equal to or are not equal to based on true and false, then you could set two different true and false bools, obviously. You could have a player bool and an enemy bool, and due to other conditional checks, maybe if you want them both to be valid targets, then you would set the true bool to true, and the, not true bool, player bool to true, and the enemy bool to true, then they'll both be true when you're doing a comparison, and then you can do your check. So that's it. That's all the compare Blackboard entries node is for. It's to compare if Blackboard entries are the same value. If you have any questions or comments, please feel free to leave them below. Is AI behavior? Oh, here's our Blackboard entries node. It is a decorator, so you can add it either to a task or a composite. And it's simple, add decorator, compare BB entries. So by default, we're going to come up with these for our settings. You're going to abort nothing, and you have no values for your key. Now, like all the other Blackboard nodes, when you first pull them up, it's going to default their Blackboard entries to whatever your first key is going to be for a valid entry. So make sure you change these to whatever you actually want to observe. So for example, what we're going to do is we're going to see if the player is equal to the... We have a player object key and an AI enemy key. Using this service here, I'm going to alternate between what the values are, and we're going to use the compare Blackboard entry node to compare them, and then do something. So let's set our player for our first key and AI enemy as our second key. And this is a pretty simple equal to or not equal to node. By default, it's set to equal to, but of course you can change it to is not equal to. We're going to set our observer up to abort nothing because that's our default. Let's go ahead and run through our example and watch our node values. When we start, our player is set to generic character, and our AI enemy was set to none. Then the player changes to none after 5 seconds, and then our AI enemy, after another 5 seconds, or 10 seconds total, will change to the AI character's value. So our compare Blackboard entry will compare and only allow the sequence to run if our values are equal. Let's set this to abort self so we can actually watch it in real time. So when we run this, what you're going to see is me not hitting the play button. We're going to see in the beginning, it ran very quickly because our values were both set to none. Then it stopped because our player was set to the player. Now that they're both back to none, it was running. And now that it's back to AI enemy, it's set to fail again. So let's go ahead and watch that again so you can watch it happen. Assuming I can hit the stop key. We have the same value as none, it ran. We have different values, it stopped running. We have the same values again as none. And then we have the different values again as none and generic AI character. And if, of course, if we were to flip this and say is not equal to, we're going to get the opposite result. We're going to watch it succeed because the values don't match, fail because the values match, and then succeed again when the values don't match. So it's pretty simple. It's a simple, and then succeed again when the values don't match. So it's we're going to watch it succeed because the values don't match, fail because the values match, and then succeed again when the values don't match. So it's pretty simple. It's a simple equal or not equal node. Make sure you have two valid values. Keep in mind this is going to be an exact comparison. You're not going to be able to, for example, I have a bool value here, and I set this to is player equal to true bool, and I run it. Actually, we'd want, yep, is equal to, okay. And run it. It's going to fail because true bool is a Boolean value, and its value is different than whatever's held currently in my player and my enemy. So keep that in mind. Now, if you wanted to use, if I can go back to it, this to compare if two things are equal to or are not equal to based on true and false, then you could set two different true and false bools, obviously. You could have a player bool and an enemy bool, and due to other conditional checks, maybe if you want them both to be valid targets, then you would set the true bool to true, and the, not true bool, player bool to true, and the enemy bool to true, then they'll both be true when you're doing a comparison, and then you can do your check. So that's it. That's all the compare Blackboard entries node is for. It's to compare if Blackboard entries are the same value. If you have any questions or comments, please feel free to leave them below. Bum 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 bum. Bum bum bum. Bum 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 bum. Welcome to video 4. What is AI behavior tree decorator? The cone check node. Let's go ahead, cover the cone check node, and jump right into an example of how it works. So the cone check node, like other decorators, can be added onto a composite node or a task node by right-clicking, going to add decorator, and choosing the decorator you want. In our case, we're going to add a cone check. Well, by default, these are the settings that you're going to see. Like other decorators, when you add them to another node automatically, the first time you click on it, it's going to try to fill in the appropriate information based on Blackboard values you have available. But by default, it's going to be none, so you're going to have to make sure that we set these up properly. Now, let's go over our settings. The first one is going to be our cone half angle. Basically, it's half of the angle of the total cone. So for example, if you wanted it to be 180 degrees, then your half angle is going to be 90. A 90 degree cone is going to be 45 degrees. And it conveniently shows you the actual cone check angle here, down in the decorator itself. We have our normal flow control for if it aborts itself or nothing. Of course, set that as needed. Now, the unique conditions for here are the cone origin, cone direction, and observed. Now, technically, it's highly annoying. It does say if it's going to be a location or an actor for some of these, you're going to need vectors. They're the only thing that's going to work. So in our case, what I've done is I have our decorator example service that I'm using here. What I'm doing for our cone check is every time we run our service, I am storing where the player currently is in the player location key. I am then storing when we start where the AI controller is, his location, as well as his forward vector, so we know where he's looking forward. Now, I'm not updating these in real time. For example, we're just showing how the cone check works, but in a real use case scenario, you would more than likely have these updated whenever you do some aggro checking or something like that to make sure your player and your artificial intelligence enemy have the appropriate line of sight. So, I've gone ahead and set up this cone check decorator here. Our origin is where our AI is currently at. Our direction is the forward vector of our AI. And the observed is going to be our player's location. The only one of these, like I said, that will update in real time is going to be our player location. So that way you can actually see the decorator here. Our origin is where our AI is currently at. Our direction is the forward vector of our AI. And the observed is going to be our player's location. The only one of these, like I said, that will update in real time is going to be our player location. So that way you can actually see the cone check working. Now, inverse condition basically is inverse condition. If the player is in our cone check, this is going to be true. If we check this, and our player is inside of our cone check, it's going to end up being false, because we've inversed it. The use case scenario for this would be, we want to see where we want our AI to activate when they see the player. That is our normal condition. We want our AI to activate when it can't see the player. That is the inverse condition. Maybe you have one of these set up where if they see it, they then aggro. Or you set up another cone check where if they can't see the player, now they're going to go ahead and run and hide or do something like that. You're going to make sure that they're in a safe location. So that's what you would use that for. Let's go ahead and pull out our decorator and try to set it up so we can see it. So here's going to be our sequence here. You're going to see when we fire this off, I'm going to go ahead and play. And by default, because we're inside of our cone, it's running the cone check successfully. If we were to go over here, you're going to see it fails. I'm running my example service every roughly 0.2 seconds, or 5 times per second. That way for this example, you can actually see it work in action. If I go over to our cone, you're going to see it works. And if we go outside of our cone, you're going to see it stop work. Our cone is roughly 180 degrees from that corner to this corner, which is why this is basically the backside. So right now, cone check is failing. They can't see me. Cone check is succeeding, and they can see me. So that is all there is to it. The cone check is just a basic, simple way of doing a cone check inside of your behavior tree. without running any custom code. You can, of course, do your own service that does the cone check for yourself. Maybe you just want to see if they're in front of it. You do a forward vector check. But if you want something simple, basic AI, where you're seeing if something is within the visibility of something else, you can use the cone check, and these are the options for it. If you have any questions or comments, please feel free to leave them below. Bum 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 bum.
Tomatoes?
Hello, welcome to Success Node. So, our force success node decorator, the force success node. So, our force success node is really simple. The goal is to allow it to force the success of anything it is attached to. Now we'll go ahead and we'll attach it to the sequence node, and we're actually going to see it not work. Two things. Force success is intended to only be used with sequences, because sequences are intended to run left to right, and will continue until you get a failure. Whereas selectors will run left to right, and will stop when you get a success. So forcing success on a selector is kind of pointless because anything after it will never run anyways. Now if we were to run this, we're actually going to see it not work like I said. We're going to see it go through, wait 3 seconds. Now when you attempt to do the play sound task without a sound, it's going to fail. And that's why you notice it blipping and then immediately going back and never finishing. Now you wonder, we have force success here, why is it not working? Well, the force success node itself really isn't going to do anything when it's on the actual composite sequence node. It's more intended to be used when it is on the task itself. So let's go ahead and see that in action. Let's remove it from there. Let's go ahead and add it to our task node itself, and we're going to run this, and we're going to see something slightly different. We're going to see, even though it fails playing the sound, it's going to continue on because it's forcing a success roll, and it's going to go to our next task node. And you'll see this repeat continually, even though we have a failure here with play sound. So that's it. It's useful, for example, if you want to force a success on an optional branch, or you want to force a success when you may not have something set up completely, but you still want it to do everything. Maybe it just won't do part of it if it's a failure. But the fail condition isn't damaging, it's just maybe do nothing if it fails. Like in the case of play sound, nothing happens. So that's it. That is your force success decorator node. If you have any questions or comments, please feel free to leave them below. So, our force success node is really simple. The goal is to allow it to force the success of anything it is attached to. Now we'll go ahead and we'll attach it to the sequence node, and we're actually going to see it not work. Two things. Force success is intended to only be used with sequences, because sequences are intended to run left to right, and will continue until you get a failure. Whereas selectors will run left to right, and will stop when you get a success. So forcing success on a selector is kind of pointless because anything after it will never run anyways. Now if we were to run this, we're actually going to see it not work like I said. We're going to see it go through, wait 3 seconds. Now when you attempt to do the play sound task without a sound, it's going to fail. And that's why you notice it blipping and then immediately going back and never finishing. Now you wonder, we have force success here, why is it not working? Well, the force success node itself really isn't going to do anything when it's on the actual composite sequence node. It's more intended to be used when it is on the task itself. So let's go ahead and see that in action. Let's remove it from there. Let's go ahead and add it to our task node itself, and we're going to run this, and we're going to see something slightly different. We're going to see, even though it fails playing the sound, it's going to continue on because it's forcing a success roll, and it's going to go to our next task node. And you'll see this repeat continually, even though we have a failure here with play sound. So that's it. It's useful, for example, if you want to force a success on an optional branch, or you want to force a success when you may not have something set up completely, but you still want it to do everything. Maybe it just won't do part of it if it's a failure. But the fail condition isn't damaging, it's just maybe do nothing if it fails. Like in the case of play sound, nothing happens. So that's it. That is your force success decorator node. If you have any questions to be used with, you're not going to get the desired result.
I'm a master of myself, and nobody else.
Bum 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 bum. Hello, welcome to the video for what is AI behavior tree, the decorator Blackboard node. I've gone ahead and set up a basic behavior tree sequence here. If we go ahead and run this, we're going to find it's going to travel down our left side. It's going to run our sequence, wait 2 seconds, wait 10, wait 2, wait 10, and it will continue indefinitely, regardless of anything happening inside the actual behavior tree itself. So let's add our decorator node. We can go on any sequence or any task, add decorator, and add our Blackboard decorator node. What we're going to do is, by default, let me reset this to none. Your Blackboard key is going to be set to none. Now, if you pull up a Blackboard node, it's automatically going to set itself to the first Blackboard key if you have one available, and I do in this case. So keep that in mind. You need to set two things for the most part to have the actual Blackboard node work properly. One of them being your Blackboard key. What is going to be checked inside this decorator node? In our case, it's going to be the player. What do we want to check? Well, we want to check and see if our player is set or is not set. Simple as that. Set in this case means there is a value in there. It's not equal to null. It's not equal to nothing. And is set means it is equal to null or is equal to nothing. So in our case, we want to make sure our player is set. Now, for example, I'm using the example service I've created here. And what this does is it's going to go ahead and find the player, set them as the player object, and then wait 5 seconds. After 5 seconds, it's going to set the player object to nothing. So it's an easy way of observing this Blackboard node. Let's go ahead and run this. And we're going to go ahead and see it run. Now on the left-hand side, we're going to see this working. Based on the player being set, it runs the information below it. It runs this sequence. So it runs wait 2 seconds, then it runs wait 10 seconds. And then it reevaluates the sequence node, and then it will continue on. Now in this case, if we look down here at our player, we're going to find when this starts, it's going to be set to null. After 1 second, I set the player, and then it goes ahead and it fires off again. So when we watch this, oops, let's hit play, and watch the bottom right, we have a player here. This condition is now valid, and it runs our nodes. But now if we look, we have no player. But because we're in the middle of a task without any way of aborting it, it's going to finish those 10 seconds before it fails this check, and then goes on to our next selector node. So what can we do about that? Well, that's what our observer aborts section is for. So we discussed this in the general decorator video. I'd want to set this to self. Now what we're going to see happen here is this is going to run because it's successful. When this changes to none, it's going to fail immediately. This is going to turn into invalid. When this changes to none, it's going to fail immediately. This is going to turn into a valid none. And then it's going to run our next node in our selector. Because this will continue to fail, this will never fire again. Our player is now set to none. We are saying only run this if our player is set, and it's going to continue to fail over and over and over. So, the other option is not set. And basically you can think of this as, is this value true, or is this value false? Is something there, is something not there? And you can't technically use true and false because true will return a valid value. A bool will return a valid value of true or false. This has to be done with a key that has a no value. It cannot be done with something that has a valid value like a bool. A class could be nothing, an object can be nothing, but vectors, rotators, floats, bools, all will have default values even if they're a 0 for the value. So in this case, if we set this to is not and we run it, what we're going to do is we're going to find it successfully ran in the beginning because we didn't have a player. And then after 1 second, our service gave us a player. This reran again and it said, oh, well, we've got no player. We've got a player now, so we're going to fail. When it failed, it went back to this node. And then after this node ran a few times, our service said, well, here you go. We don't have a player anymore. This reran again, the condition, and said, oh, we have no player again? Okay, let me have it back. So if you watch it, you're going to watch it flip-flop between the left chain, no player, right chain, player, and then back to the left chain once we have no player again. So keep in mind, these will reevaluate every time it comes back to here. So in terms of our case here, this fails, comes back to here, runs the next one. This finishes, goes back to here, runs this node again. And remember, that's the way selectors note. Every time it runs, it goes from left to right until it finds something that runs. Then it comes back up and goes left to right. So the other options. Now, we have our on result change and our on value change. These are going to cause a little bit of confusion, so I had to rig this example up in a specific way to show it. Result change is whether or not the result, which is here when we're running, let's go ahead and run this, is changing from a valid to an invalid result. So right now it's valid, generic character. Now it's invalid, none. That is a result change. When the result change happens, then the observer fires off, and then this runs. We're going to abort itself. Now, if I was to change this to value change, and I ran this, what you're going to see is if the value changes down here, this is immediately going to fire. Now, you may be thinking, what is value? What does that mean? Well, this is what the value is. I've gone ahead and changed our service here to, instead of making it null and no object, to make it the pawn itself, the AI. What's going to happen when we run this now is you're going to see our value here change from our generic character to the generic AI character. Now, this isn't going to work because I have this set to is not. We set this back to is set player. We set this to result change. Let's go ahead and watch what happens here. So this is going to start running. We have a generic character here. Then it changes to generic AI character. Now if you watch these nodes, you'll notice it's still waiting 10 seconds. Even though we told this on the result change to abort, it didn't abort because our result did not change. Our value changed. So if we watch this again, what you're going to see is it waits 2 seconds, waits 10 seconds, waits 2, waits 10. In the middle of our waiting 10 seconds, our value down here will change, but we will continue waiting 10 seconds. Let's run that and watch. So our value down here is generic character. We'll be in wait 10 seconds, and now it's generic AI character, and we're still waiting 10 seconds. Nothing happened. We change this to value change, and we run our example. What you're going to see happen is when this value down here changes to generic AI, this will abort and go back to our starting sequence. So this aborts based on the value being changed and starts over because, remember, our value is the value it holds and our result is the result if it's good or bad. So that's something to keep in mind. An example of that is if you have a service here and the service is finding a valid target. If it finds no target at all, you may want it to stop moving. If it finds a different target, you may want it to then move to the different target. So you need to keep that in mind. The value may be a different target. The result may be if you have a target or not. So that's it. That is how our decorator Blackboard node works. It's very simple. Its intention is to watch Blackboard values and do something based on the result. If you have any questions or comments, please feel free to leave them. Hello, welcome to video 4. What is AI Behavior Tree Decorator, the loop node? Here is our little example. We're going to go ahead and cover what the loop node does. So our loop node is pretty simple. You can access it like any other decorator from either a composite node or a task node. You can just right click, add decorator, and in our case it'll be the loop node. Now by default, this is what you're going to find on the loop node. Number of loops, defaulting to 3, and the infinite loop checkbox. And it's pretty simple. Basically, anything this is decorating will loop that many times before it continues on. Before it returns a success value. So in the case of a sequence, where things are done in order, this is going to run 3 times, and then this will run once, and this will run once. Now as an example, if I move the loop node over here to my move to, it may not work how you'd expect it. Move to will run, it will get to its acceptable radius, and immediately fire in its success. Now with the loop on here, it's going to fire 3 immediate successes in a row before it moves on over here, so you're not going to really see any difference. It's useful for something like maybe a wait, or you want to play a sound and then wait after that and you want the sound to continue to loop, or maybe you want a continuous move to and you want it to just continually loop. Now, the number of loops basically determines the number of times it loops. So if we run through our example here, what we're going to see happen is this says loops remaining 2, loops remaining 1, loops remaining 0, and then it's going to move to our next sequence. Move 2, wait 5 seconds, and then it's going to repeat. Keep in mind, once this successfully finishes, this is considered successful. It'll go all the way back to our root, and then our root's going to fire back down. Everything's going to start over from the beginning. We're going to run this wait 3 times because of our loop, run our move to once, our wait once, go back to the top, and then fire it off again. Now here's something to keep in mind. If you have this set up for an infinite loop, and you don't have any way to break out of it, it's going to continue. You're basically just creating a selector with only one branch, and you're not really going to ever see the rest of your sequence. You'll notice that we do not have the number of loops left anymore, and it's just going to simply continue indefinitely. So make sure you have something like a Blackboard decorator or something above it, so that way it can break out of the entire sequence. In this case, I can go ahead and set is AI enemy set to allow this to run, and when AI enemy is not set, it's going to break out of my loop. So if we run this, it should run 3 times, move, wait, and repeat. Even though I have this set to infinite, the difference that's going to happen now is it's going to abort out when this fails, and then our AI enemy itself, well, sorry, it's going to abort out assuming I tell it to. There we go. Now we should see the required observed. This will run, this will change to none, this will abort self, and our infinite loop now is no longer infinite because we no longer have a valid enemy. And to show you that working, if I unhook the infinite loop, and I was to go ahead and run this, we'll see it work like we want to, but because this is set to abort self, we're going to get halfway through our move 2, and then it'll abort and the whole sequence will stop. And there we go. So that is our loop decorator node. It's useful for looping something. It only has a few parameters. Make sure if you're going to set it up as an infinite loop, you have some way of escaping out of it. And it's primarily useful for looping through individual tasks and things like that. If you have a question or a comment, welcome to the video for what is AI behavior tree, the decorator. First of all, the composite decorator node is not the same as a composite node. In this case, it's using composite to mean combination or combining, not necessarily of this funky gray composite node. So now that we got that out of the way, what do we use the composite node for? Well, it's useful for giving a little bit of advanced logic, but not necessarily fully complete like a full blueprint. It's mainly intended for you to add decorator nodes together using AND, OR, and NOT nodes to create more complex logic. So, like any other decorator, you can add the decorator to a task or to a sequence. Let's add one here. We'll go to the composite, and you're going to see our composite node right here. Now, by default, your composite node has no settings except for the name, because the composite node has its own event graph. If we double click on it, we'll now find the event graph. By default, you're only going to have an in result, input for a result, and every composite node needs a result on whether it's true or false. So let's go ahead and look at one that I have set up here. Let me delete the example, and we'll look at this composite node. What I've done here is I've made a simple AND check. Is our player set? Right here, and it's a Blackboard node, and it's set to is our player set. And then we have another Blackboard node, is our AI enemy set. We AND them together and put out the result. You can right click and you'll see all of our normal decorator nodes, including any custom decorator nodes you may have created. And this allows you to do some basic AI. Maybe you have, is your target to follow set, and can you find a path? And then you want to do the AND result out. So, for example, I've done these two, and like I said, you have logic nodes AND, NOT, and OR. So, let's run this and see what happens. If I go ahead and run this example here, what we're going to see is right now I have my player set to something and my AI set to nothing, and therefore that was failing. Now that my AI and my enemy were both set, this was running. Now my AI is back to not set, but of course this is continuing to run because we haven't set an abort condition. So to watch that again, the way I've set this up is at 0 seconds it's going to set the player, at 5 seconds it's going to set the player and the AI enemy, and at 10 seconds it's going to remove the AI enemy. So basically you have your player finding the enemy and then destroying the enemy. And with our decorator, we have it set up where we need both of them to be valid. Once they're both valid, it's going to run. It's going to run any tasks I've set below it. And then once it's invalid, it's supposed to abort. Well, it will become invalid once we've finished any sequences we're running, which is why after 10 seconds, you see it fail back up the chain. And of course, now it's not going to run anymore because we don't have valid player is set and enemy is set. Now, if you notice here, there is no aborting sections on our actual node. Well, those are inside of the composite node itself and on each of the individual settings you have set up. So in our case for a Blackboard, we have our normal Blackboard notification settings. We have the notify observer on result and value change, and then what aborts. Any other node is going to have the standard ones, like our cooldown here, it will have the observer aborting after cooldown time. So for our example, we want to abort immediately when the enemy is no longer valid, so we just simply change it. When the result changes for the AI enemy, we abort self. We'll go ahead and save it. We'll go back to our behavior tree, and now if you read it, you can see if the Blackboard player is set and the Blackboard AI enemy is set and the AI enemy is set to abort self, then we're going to go ahead and run this. Now, one thing you may have noticed is sometimes maybe this gets a little bit big. You have the option to show operations here, If you have it checked by default, you'll see this. If you have it unchecked, it's going to go ahead and hide it and just leave you the title of what it is. So that's something to keep in mind if your nodes are starting to get pretty large. So let's run this again. Now that we've set up the abortion, we'll run it. We're going to find nothing happens because we do not have a valid composite node. We have a valid composite node it runs. When this becomes invalid, it's going to go ahead and abort because we've set it to abort. And of course, go back up to the top and then continue failing because this is no longer a valid composite node. So that's it. That's what a composite node is good for. You can think of it kind of like your macros and your functions where you're trying to condense things into more compact. I mean, because technically you could do 5 different blueprint nodes in here with different is set, is not set, and different things like that. Or you could do a simple composite node, combine things together, and then have your desired result. And of course, because it's a composite node, you can go ahead and you could use this in a different section, copy and paste it. You have all of your logic here, so things work out easier. If you have any questions or comments, please feel free to leave them below.
Wenn aus undenkbar undenkbar wird, dann wird
Tomatoes
is AI behavior tree decorator, the time limit node. Let's go ahead and let's watch this time limit node in action, then I'm going to explain how it works. For the most part, you're basically going to see this branch run until the time limit's hit, then it's going to fail, roll back over to the next lower node because we're using a selector. Let's go ahead and run this. You'll notice this time limit counts down while the things under it run. Once it hits 0, it will mark itself as a failure, and then the next thing will happen. Because we're using the selector node, the selectors will continue on until they find a success. So when this fails, it doesn't go all the way back up the branch, it simply goes to the next part of the selector. Now when this part of the branch, of course, succeeds, because it's good for 5 seconds, our selector refires, and we get this to fire again, counts down 5 seconds, and then it repeats. Now, the time limit is a decorator node. You can find it by right-clicking on any composite node or task node, and then you want to look for, all the way at the bottom, the time limit. By default, it's going to come with 5 seconds, and that's really all you can adjust. You do have the observer aborts, but it is set to self and only allows self. So, let's go ahead and watch what happens if we hook this up to a sequence node. Hopefully, you should be able to determine what's going to happen before we even run this. So, the sequence node, when we run it, it's going to do the same thing as before. It's going to count down the 5 seconds, it's going to fail, but then it's going to re-trigger itself again. Keep in mind, sequence nodes continue until you get a failure, then it fails up the tree, and then comes back down. And because that's happening, we're never going to see our other branches, and it's just simply going to keep repeating. So keep that in mind when you use a time limit node. It's not just simply finishing and then moving on. It will fail after that time limit, and that's why it says failed after 5 seconds. So it's a good way to force something not to continue forever, but still maybe do a little bit of an action, and then in line with a selector node, you can go ahead and continue on until you get a good result, and then come back and do something again. If you have any questions or comments, please.
Tomatoes
What is AI behavior tree decorator? The is at location node. Let me go ahead and switch over to our example, and I'll show you how it works. So right now, I have a little AI character, and he's basically emulating a simple follow me movement. I'm using the is at location to constantly check and see if he is at the location of my player. If not, I move him to the location of my player, and then it continues indefinitely. If he's at the location of my player, then he stops, and he does nothing. So let's take a look and see how that works. So our is at location decorator, like any other decorator, can be attached either to a composite node or a task node by right-clicking, adding decorator, and you can choose is at location. Now by default, is at location is going to come in with no Blackboard key, but of course the first time you click on it, it's going to default to your first valid location. Now the is at location wants a location, a vector, and that's what it's going to use if this pawn that you're controlling with the AI behavior tree is at that location. Now for the nodes itself, the parameters, we have acceptable radius, use nav agent goal location, and inverse location. Basically, the acceptable radius is the radius from its origin point to your goal location and whether it is within that radius. This is something important to keep in mind. By default, you're going to find 50 as your acceptable radius. Now if I run this, you're going to see something happen. Now it looks like our player has reached our goal. Our enemy has reached us. If we look at this, you'll see it's still running. Well, the problem is 50 is in centimeters, and our player itself is around 50, along with our AI itself, and it's not big enough. If we were to change this to 100 and run it again, you're going to notice the AI comes over to us, and you're going to notice the behavior tree has stopped running, and is at location inverse has failed because we are now successfully at our goal. So, use nav agent goal location. Basically, if we're moving to an actor, and this actor is a navigation agent, then we'll move to their nav agent location. This is a way to find other actors rather than locations. Now, it doesn't really work properly for whatever reason, but by default it's turned on and you should use it. Inverse condition basically flips the check. The check by default is, are we at this location? And if so, execute our composite node. Since we want to see if we're not at the location and move to it, we use our inverse. So if I was to run this as it is now, we're going to find it's going to fail because our player location is here, and our AR location is here, and of course they're not the same. So because they're not the same, is at location is not true, and our node is not going to execute. We flip this, and as you can see here, we have a really simple follow AI. Every time my selector primary fires, every basically 0.2 seconds, the player's location is updated. We check to see if our pawn is at that location, and if it's not, because we have it inversed, we go and run our sequence, which is a simple move to player location. Now the other option on here is slightly essential. It is our Blackboard key, and this is where you need to put in your vector, which is the location you will be going to on your is at location check. So we're basically going to check and see if the attached pawn, its location, is equal to or not equal to the Blackboard key value here, which is a vector 3, and then the sequence executes. So that's it. That is what an is at location is for. There used to be the reached move goal node. It was replaced, it was removed technically, and then the is at location was used. So if you are referring to older documentation, you may see the reached move goal that is no longer available. We're now using the is at location node, and those are the documentation for the is at location. If you have any questions or comments, please feel free to leave them below. Hello, welcome to the video for what is AI behavior tree. that's also a lot of fun to use, so let's cover how it works. Now our cooldown node basically only has two different parameters. We're going to have the cooldown time, and then if the observer aborts. Now your observer aborts is only going to have none and lower priority, because this isn't something that really checks to see if a condition is met. The point of the cooldown node is to prevent a branch from running for a certain amount of time after it's gone ahead and successfully ran properly. So let's see how this works. I have our cooldown node set to 5 seconds, and I have a wait node underneath it for 3 seconds. So the normal execution here without the cooldown node would be it runs from our root through our selector, our sequence runs, which will be wait for 3 seconds, and then the whole thing's going to fire again. So we're going to continually firing off this task every 3 seconds because we have a wait set up. Well, let's say this task was, for example, firing a bullet or looking for the player. Maybe you want it to only look for the player every second, so that way it's not constantly having eagle eye. You have an easier enemy, so its aggro check is delayed. So let's say you have this set up at 3 seconds. But let's say after it looks, it gets bored, and it's no longer going to be alert, and it's going to do nothing for 5 seconds. Well, that's what our cooldown node is for. So what happens here when we run this is we go through our normal setup. The wait node runs, which means 3 seconds it's going to wait, and then it fires back up to our root. Now the difference here is once this successfully finishes, our cooldown node fires. Now it will lock and return a failure for this branch when it fires for the duration you've set up as the cooldown time. So as you notice, we wait 3 seconds, it goes back to the top, our cooldown fires, it locks this branch for 5 seconds, and then it allows execution after 5 seconds. And that will continue indefinitely because that's what the cooldown node is for. It is a cooldown. That's it. Like I said, this was a really simple node. It's intended for locking off branches, and you can use it as a way to maybe spice up the variety of things, give your players a little bit of breathing time, have built-in cooldowns in your AI itself without resorting to actually needing a service to restrict branches from running. If you have any questions or comments, please feel free to leave them below.
Wenn aus undenkbar undenkbar wird, dann wird aus mal eben einkaufen das Klimaschützen.
Bum 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 bum. Oh, welcome to video 4. What is AI behavior tree decorator, the keep in cone node? Let me run through a quick little example, and then I'll break down how the cone itself works, the cone node works. We have our enemy AI. Now I've added a little green dot so you can see the front forward-facing direction. Now my behavior tree right now is designed where every 5 seconds it's going to go ahead and try to move to the player. And if you are no longer inside of its cone, it will immediately abort, waiting for 5 seconds, and then immediately go to the player. So if I was to move back, you're going to notice it moves after me. I move back, we wait 5 seconds, it's going to move back after me again. Now if I was to move behind it, it's going to immediately stop waiting and come find me. Because I've set the cone check to 180 degrees and it's constantly observing. And once I get past that 180 degree mark, the cone check is going to fail and it's going to come after me. So how does this work? Well, the keep in cone node has a few parameters and we'll cover them now. Remember, you can access any decorator nodes by right-clicking on the sequence, the composite. I hate that name. You can access any of the decorator nodes by right-clicking on a composite node or a task node. In this case, we want to select the keep in cone node. Now our keep in cone node has these following parameters. Cone half angle, by default it's going to be 45 degrees, which means you have 90 degrees total. 45 degrees to the left of the front and 45 degrees to the right of the front. Unlike the cone check, this one automatically looks forward based on what you're observing when it starts. Now observer aborts is set to self and you cannot change it. Our two primary options are going to be our cone origin and observed. Cone origin is going to be the origin of our cone, where it starts at. What is looking through this cone. Observed is going to be what we are looking at, or our target. In this case, my origin is going to be our enemy, and our observed is going to be our player. And we want to make sure our player is in that cone of sight at all times. Let's go ahead and open this up so we can observe it while it's running. So here's our settings. Let's make it a little bit wider. And we'll go ahead and check this out. Let's run this and bring this back into view. Oh, I don't even need to bring a view. I can bring this side. There we go. So we have our player, and as you can see right now, we are waiting. It's going to run our services, do our decorator node. If keep in cone is valid, it's going to go and run our sequence, which is a move to player, and then wait 5 seconds. And as you can see, since we're already at the player, it'll flash every 5 seconds really quickly through the tree. Now, if I was to move backwards you're going to notice our wait node is just going to sit there, and then we'll fire our sequence, and our move to player will activate. And that'll repeat indefinitely. If I was to move outside of our cone range, which in this case is 90 degrees, you're going to notice our wait node is going to immediately abort. And our move to player is going to fire. So that is what the keep in cone degrees node is just going to sit there, and then we'll fire our sequence, and our move to player will activate. And that'll repeat indefinitely. If I was to move outside of our cone range, which in this case is 90 degrees, you're going to notice our wait node is going to immediately abort. And our move to player is going to fire. So that is what the keep in cone node is and what it's intended for. It's intended to allow you to basically control this branch based on if something is inside of that cone of sight. If you have any questions or comments, please feel free to leave them below.
Endori.
Bum 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 bum.
Tomatoes?
Hello, welcome to the video for what is AI Behavior Tree Decorator, the Does Path Exist node. So I fired up a quick little example. We're actually going to run through the example, and then I'll cover how the node works, and we'll see it in detail. So for my example here, I have a AI enemy that is moving to my location, waiting through seconds, and then moving again. But it's using the Does Path Exist to make sure that it has a good path to path on every time it needs to path. Now this little section over here I've set up where the nav mesh does not cover. And you'll notice our player, our enemy, cannot get to the player, therefore he's not even going to try. It's going to abort on that behavior tree. If I go back to my movable area, you'll notice he'll move over successfully. And to demonstrate that, you can see here's my nav mesh, and here's the unreachable nav mesh area that is set up to not be reachable. So let's go ahead and look at the decorator and see how it works. Keep in mind, decorators are a way to basically program your behavior tree without having to need services and other things that can duplicate, but with less code work. I mean, it's a simple helper node. That's what it's for. So let's see how it works. Now, by default, we're going to come up with these following values for the Does Path Exist node. Decorator nodes can be added to any composite node or any task node by just right-clicking, add decorator, and then you can find the Does Path Exist node. So in our case, we need a Blackboard key a Blackboard key B, and then what type of path it's going to use. So for my example, I'm setting up the location of the AI as the Blackboard key A, and then I'm setting up the location of the player as Blackboard key B. Now, path query type basically has three settings. From top to bottom, you have their speed. Really fast, fast, and slow. By default, it's going to default with fast, and of course, unless you really need the extra performance from this node, you can go ahead and leave it as such. Inverse condition basically flips the check. Right now, if a path exists, this is going to continue on. If we use inverse condition, then it's going to reverse the condition check. It's going to succeed if the path does not exist. So you may have one here where it moves, and then you may have something else, for example, where if it fails, it's then going to maybe wait 10 seconds to try to find a different path, or maybe it explodes. Maybe you made a mouse trap, and once you've successfully trapped the mouse, you no longer want them to do anything, so you set it up where it dead ends, and they have no valid path, so there's no point in checking any other further AI. So that's how you would use the inverse condition checkbox. Under that, we have our normal things, such as flow control, which allows us to change when the observer aborts. And then we have the node section for the navigation mesh. By default, if you set it to none, it's going to use the default filter on your nav mesh. If you have multiple navigation data, then you can choose which navigation data it will use for the move to and checking if the path exists. If you are doing multiple navigation meshes with navigation data, you will know if you need to use that or not. By default, leave it at none. Most people will only have one set of navigation data. So let's watch this working. Let me drag this back over and pull it down. And we're going to go ahead and watch this in motion. This is extremely large. Let's see if we can, let's see if we can stack it up like that. There we go. Okay, so when we go ahead and play, you're going to see we have a valid move to location. Once it gets there, it waits 3 seconds because that's the way we have our sequence set up. You'll see it move to me. Once it gets there, it waits 3 seconds, and then it will move toward me, and then wait 3 seconds. Now, if I move over here, we're going to see an issue. When it attempts to do the path does exist, which is right here, you're going to notice this red mark because it failed. It is not able to find a valid path from the enemy to myself because there is no valid navigation mesh that lets it move. Once I move back over here, you're going to find it fires off again, and it runs successfully. And it will continue, of course, until it can no longer find a valid path exist. When, of course, I fall off, so that makes a super failure. Now, in this case, this is where it's kind of funny. You're going to notice it's actually working. I'm not doing any validation checks. This is a generic example. What you're seeing is the AI location attempting to get to the player's location of 0000, which technically has a valid path, and that's why it will continue moving. So, in this instance, make sure you actually have valid sanity checks, like when you kill your player, do other checks in your behavior tree, like does the player exist, then do your AI. And for example, it shows that using the path exist, because you're using a location to a location, you always want to have some sort of sanity check in front of that to make sure, even though you have two valid locations, make sure you actually have a reason to do it. So that's it. That's what our does path exist decorator node does. If you have any questions or comments, please feel free.
Die Chicken McNuggets mit 100%.
Hello, welcome to video 4. What is AI behavior tree decorator? The is BB entry of class node. So let's go ahead and cover this. First of all, that's a long, annoying name, but it's short for, is this a Blackboard value of a given class? Now you can access the decorator from either a sequence or a task node. You can right click, add decorator, and this one's shorthanded to is BB entry of class. And this is the result you're going to get. Now by default, of course, you're going to have none for the key, but whenever you click on a decorator the first time, it's going to try to find a valid match. Now your class itself is going to be set to none, your Blackboard key will be whatever your first match is, and then your observer reports will be set to none. Now what would we use this for? Well, this is basically a way to check and see if the class you're testing against matches a Blackboard key's value. So for my example here, I'm going to go ahead and show you it working. I have my generic character, which is my player, and then I have my Blackboard key of player. Now if I go ahead and run this, what you're going to see is, well, it works. It works like expected. It checks my service here is updating my player object with player. It's a generic character. This is checking to see if it is of type generic character for the player, which it is, and then it runs my sequencers, which is a move to. Now since I'm not using any other decorators to make sure we're already there and things like that, it's going to keep continually trying this loop. Now what would this be good for? Well, let's say for example you have multiple enemies in your game, and you only really want to use one behavior tree, but some enemies have different parameters, or some enemies have different abilities that you're allowing them to use. Well, you can segregate and use one behavior tree for multiple enemies by using the is it of the player class. So let's say for example we had this here, and let's say we had another sequence here, and we put our is BB entry of class. Let's actually choose the right one, and then we'll have this one do a move to as well. And we'll have this moving to the player's location. Actually, that would be funny if you had the player move to the AI and the AI move to the player. It would just be rounding in circles. But that was slightly off topic. So let's say you have your AI, which apparently I cannot spell. There we go. So let's say you have an AI character. Right now, for example, we only have one, but let's say you had 5 of them. And let's say each one of these is a different one. Let's go ahead and we'll set this one up so it fails. We're going to make sure this is invalid. We're just going to check and see if our player is equal to... do we have a box in here? Let's see if the player is equal to a scale box. Why not? And if so, it's going to execute the sequence. Now, if not, it's going to go ahead and execute this one, which is a Blackboard value of a class. And we're checking if our AI enemy, which is our self, which we've stored here, is equal to generic AI character. And if so, we execute this node. Now, if we go ahead and run this, and we check it out, you're going to find it fails. Well, it fails because in here, I haven't set the AI character yet. If you look down here, AI character was not set. Now it is. Now it goes back to none. And you notice when that happened, this stopped running. So in our scenario here, let me run it again and let you watch it. You're going to see our AI enemy be none, and nothing will match, so nothing runs. Then we get a valid AI enemy, so this branch runs. And then our AI enemy disappears, which means this branch will now fail. And since both of them fail on our selector, we go all the way back to our root. So let's run this. Everything's failing. None for the AI enemy. We get a valid AI enemy. We're now running this branch, since this branch is invalid. Our AI enemy will become none again. Once this finishes, we go ahead and it goes back to the top. Now, if I want it to abort normally, you can use your flow control for observer aborts, and I could abort immediately, for example, if it immediately changed. So that is what our is Blackboard value of class, or in shorthand in here, it's the is BB entry of class decorator node is for. It's for comparing a Blackboard entry against a class and seeing if they are the same. And a good use for it, as you can see here, is to allow you to have one generic or universal behavior tree that has different behaviors depending on what you're testing against. In this case, each of these could be enemy 1, enemy 2, enemy 3, and you wouldn't have to rewrite the same basic AI or behavior tree for everything. Now, if you have any questions or comments, please feel free to leave them below. Decorator, and this one's shorthanded. You're going to have none for the key. Your class itself is going to be set to none. Your Blackboard key will be whatever your first match is, and then your observer reports will be set to if the class. I'm going to go ahead and show you it working. I have my generic character. What you're going to see is, well, it works. It works. It's a generic character. This is checking to see if it... Now, since I'm not using any other decorator, now what would this be good for? Well, let's say, for example, you have multiple enemies in your game, and you only really want to use one behavior tree, but some enemies have different parameters, or some enemies have different abilities that you're allowing them to use. Well, you can segregate and use one behavior tree for multiple enemies by using the is it of the player class. So let's say, for example, we had this here. And let's say we had another sequence here. We put our is BB entry. Oops, of classes. Yeah. So let's say you have an AI. Let's go ahead. Let's see if the player execute this one, which is a Blackboard value of a class, and we're checking if our AI enemy, which is ourself, which we've stored here, is equal to generic AI character. And if so, we execute this node. Now if we go ahead and run this, it's going to execute the sequence. Now if not, it's going to go ahead and execute this one, which is a Blackboard value of a class, and we're checking. Now let's see if the player is equal to a scale box. Why not? And if so, it's going to execute this sequence. Now if not, it's going to go ahead and execute this one, which is a Blackboard value of a class, and we're checking if our AI enemy, which is ourself, which we've stored here, is equal to generic AI character. And if so, we execute this node. Now if we go ahead and run this, and we check it out, you're going to find it fails. Well, it fails because in here, I haven't set the AI character yet. If you look down here, AI character was not set, now it is. Now it goes back to none. And you notice when that happened, this stopped running. So in our scenario here, let me run it again and let you watch it. You're going to see our AI enemy be none, and nothing will match, so nothing runs. Then we get a valid AI enemy, so this branch runs. And then our AI enemy disappears, which means this branch will now fail. And since both of them fail on our selector, we go all the way back to our root. So let's run this. Everything's failing, none for the AI enemy. We get a valid AI enemy. We're now running this branch, since this branch is invalid. Our AI enemy will become none again. Once this finishes, we go ahead and it goes back to the top. Now, if I want it to abort normally, in short, comparing a Blackboard entry against a class and seeing if they are the same. And a good use for it, as you can see here, is to allow you to have one generic or universal behavior tree that has different behaviors depending on what you're testing against. In this case, each of these could be enemy 1, enemy 2, enemy 3, and you wouldn't have to rewrite the same basic AI or behavior tree for everything. Now, if you have any questions or comments, please feel free to leave them below. Hello, welcome to video 4. What is the task node? That is going to be our purple task node. The bottom of our tree are intended to be the end of our branches. They're intended to allow you to just simply do a task. It's supposed to be something very simple, like for example this wait task simply waits for a duration we specify. Maybe we have a task for playing a sound. All it's going to do is take a sound and play it. Now, the tasks themselves can be accessed, as you saw, by right-clicking anywhere in your event graph, going to tasks, and choosing one of the pre-built tasks. Or, if you create your own task, like I have one here called task, it'll show up in this list as well. You can create your own tasks, or you can use the pre-built ones. All of the tasks are going to have their own parameters set up based on the task itself. You're not going to find really anything that is going to be the same between task to task. They're all unique because they're intended to serve a unique function. Now, keep in mind, the tasking is intended to do something very simple and small. You can create your own tasks, and we'll cover that in a second. But you really don't want to have something very complex. Maybe a cone check, or line trace, or a custom move to where you have a custom abort node, or it rechecks the target every so often. Even then, maybe have the move check and the target check being separate so you can string them along in a sequence and abort easier. So, let's go ahead and cover the task itself. If we do new task, what we're going to do is come up with this. It's going to be an event graph with nothing in it. Now there are 6 overrideable nodes. You have the tick, the execute, and the abort, along with the AI versions of each of these. The tick is normal. It is called whenever there's a tick on this task. The execute is whenever it's called for the first time. It's a single run, basically. It's your on begin play. And then your abort, this isn't your end play. This is when an abort is called down from a higher end node. Remember, if you're using a decorator, for example, and you have the abort option turned on, if this was to abort self, and then the abort was called inside of our task, if we have the receive abort node override receive abort event overridden, then this will get called. Now let's go ahead and show this in an example. Let me go ahead and override my receive execute, and we're going to do something simple. We're just going to print out a string, and we're going to print out that, this is our awesome task. And then we're going to go ahead and compile it, and then we're going to run it. And as you can see here, let me get rid of this, we have a simple sequence. It's going to run our task, and then it's going to wait 5 seconds. And let's run this. Now if we run it, well, we did see, this is our awesome task in the top left, and we see our sequence running. But we're not seeing anything else happen. We're not seeing it go to the next wait. We're not seeing it go back up. It's stuck. And the reason it's stuck is the task requires a finish node to be called. There are 2 of them, finish abort and finish execute. Technically, there's also finish on message and message with ID, but these are more specific. This allows a task to wait for a message in order to finish, rather than finish executing or finish aborting. Let's add the finish execute node and wire it up. We should see something different. Now when we run this, well, now we're seeing it constantly being spammed. If we go back into our sequence, you can see it is constantly running. You'll see the root flash every so often. And our task is running over and over, and we're never actually getting to our next part of our sequence. And the reason for that is we are failing. We are not successful on this, and because it's a sequence node, if it fails, it'll go back and abort back to the top. The finish execute has a Boolean node called success. So if you want to successfully execute and return a pass, you need to make sure it's checked. Now we should get our desired result. It prints out once, waits 5 seconds, and then it'll print out again. And if we go into here, we can actually see that happening. Waiting, then I'll go back and fire our print, wait again, and it will continue indefinitely. So that is the basics of a task. There are other options. There are other specific nodes for tasks themselves in here. Like for example, in the other behavior tree, you have the finish abort, the finish on method, and you can find some other things that are built specifically for the behavior tree in here in terms of a task, such as checking to see if the task is executing and aborting. And these are all handled separately. But the basics of the task is it's got the same features of a normal event graph. You can use your normal blueprint math, you could use your utilities, you can check for the player, you can get rotations, and it's just expecting you to return something out or to do something. That's the biggest key. These, if you notice, don't have outputs, and they're not really intended to set anything. These are intended to do something. A service is intended to set something, and that is covered in a different video. And that's it. If you have any questions or comments, welcome. So I've gone ahead and made a quick little example here. The make noise node itself is very, very simple, but actually seeing how it's used is a little more complicated. So we're going to go ahead and cover that. Now the make noise node is pretty simple. You access it from tasks and make noise. There we go. It's only got one setting, the loudness of the noise. Now the loudness is a range from 0 to 1, basically how loud the noise will be. And then that's a multiplier based on the other settings from the pawn emitter and the pawn sensor. So let's see how that works. Let's run this example. What you're going to see on the top left corner is a notice that we heard a noise, where it came from, and the location. So in this case, the generic AI character, and then the location from the generic AI character. What we're doing is simply waiting a second, making the noise, and then waiting 5 more seconds. Now to actually take advantage of the noise, it requires 2 things. Your AI character is going to need a pawn noise emitter. This is a component that's part of the AI section, and this is what will allow it to emit noise. Noise lifetime is how long that noise will persist for, and the other settings for the most part you can leave blank. It's nothing specific, it's just a way to alert a pawn sensor that a noise was made. Now speaking of pawn sensors, whatever wants to listen needs to have a pawn sensor. And that is right here, which is your pawn sensing component. Inside of here you have a few more examples, as well as some events that you can override. In here I've overridden the on here noise, and all I'm doing is getting the instigator's name and the location and printing out a string. Noise, where it came from, and what we're doing is simply waiting a second, making the noise, and then waiting 5 more seconds. Now to actually take advantage of the noise, it requires 2 things. Your AI character is going to need a pawn noise emitter. This is a component that's part of the AI section, and this is what will allow it to emit noise. Noise lifetime is how long that noise will persist for, and the other settings for the most part you can leave blank. It's nothing specific, it's just a way to alert a pawn sensor that a noise was made. Now, speaking of pawn sensors, whatever wants to listen needs to have a pawn sensor. And that is right here, which is your pawn sensing component. Inside of here, you have a few more examples, as well as some events that you can override. In here, I've overridden the on-here noise, and all I'm doing is getting the instigator's name and the location and printing out a string. Let's actually go ahead and up this duration to 5 seconds to make it a little easier to see. So it's pretty much as simple as that. Now here's a couple things to keep in mind. Now this is not a complete overview of the pawn sensing and pawn emitter system, but if you're playing around with this, by default, pawn sensing will only sense players. In this case, since I want to sense my AI controller, I need to uncheck this. You also have the see pawns option. To make this easier, I uncheck this, but basically, hear noises will not fire if you can see the pawn. So it's basically one or the other. So if you're playing around and you run into some issues, you might want to adjust that. Also, if you're seeing more than one message pop up, by default, your sensing interval is half a second, which means every half a second it's going to listen for a sound. Your character, by default, will make sounds for 1 second. So what you're going to see is two messages because you heard that same sound twice. You could make it something simpler like 0.5 and make all of your sensing stuff to 0.5, and then you're going to go ahead and you will only get one message. So if we run this again, we're going to go ahead and see the message. I heard a noise from generic AI character at location. And if you notice, we're seeing 2 of them because of the fact I have the noise in here somewhere emitting for half a second, and I'm listening every half a second. If we adjust it to something like that, we might have something slightly different. So that's something to keep in mind. Those are some settings you want to adjust. Like I'll put this back to 1 second sensing interval. I'll move my emitter back to half a second. We'll go ahead and play. And now you can see we're only getting 1 message. But again, we're not covering the pawn AI sensing and emitter section right now. This is just to show you that the make noise node works. It requires the emitter on your AI, so it'll emit the sound itself, and then whatever needs to hear the sound will use the pawn sensing. That's it. It's not very fancy because it's intended to just basically be a very generic node. You can, of course, override this with your own node and do some more advanced noise and AI perception stuff. So that's it. Welcome to video 4. What is? I've gone ahead, I've created a quick little example. Let's go ahead and check out how this works. So the move to task is one of the tasks that are built in with the engine currently. You can access it by right-clicking tasks and choosing move to. Now by default, it's going to have nothing for the Blackboard key, but keep in mind the first time you click on it, it's going to try to find the first valid object. If not, it's going to default to none, and it's going to have an issue. So let's check out these settings. Well, let's see how it works first. Let me go ahead and run this, and you'll see my little enemy come follow me. Then he's going to wait 5 seconds, and then the sequence will repeat, and he will move to me again. And notice with the way it's set up right now, he's actually moving to the player itself and not the player's location. So let's check out and see how that works. So for the move to, we have a couple different settings in here, and then we also have one that is a advanced setting. So for default settings, we have acceptable radius. When you're using a location for the key, because you can use location or actors. When you're using location for the key, this is the acceptable radius that it has to be within for it to consider it a success, or else it will keep trying. Now, one thing to keep in mind is this is in centimeters, so for the most part, you're probably going to want that to be a higher value. Let me go ahead and change this to the location and run it, and we'll see what happens. You'll notice it comes to me, and then when I move, it's going to move to the actual position. So watch, I'm right here on the edge. It's going to come to me, and then when I move, it's going to finish moving to where my actual center location was. And in the meantime, while it's trying to get to me, it's going to be stuck in this move to task node. Now, if you change your acceptable radius to something more like 140 in my case, and I run it again, well, notice he gets to me, and now when I move, he's not actually moving forward. And if you notice, I'll move it to the side this time, you're going to notice he's going to stop a little bit farther away because the radius is now 140. So that's something to keep in mind. If you're going to use an actual location for your key, make sure your acceptable radius keeps them from continually being stuck because they can't get into your location. Now, if your location is a actual exit point or something like that where there's nothing obstructing it, then it's not an issue. Now, filter class. Filter class is the setup for your recast and your nav mesh data. If you're using the default nav mesh, you don't have to change this. If you're using custom nav mesh data or multiple nav meshes, you will know, and then you will know you need to change this. So it uses the correct nav mesh data for this AI. Allow strafe is simple. It allows the person to strafe, well, the AI in this case, to strafe rather than rotating and going forward. So by strafing, it does allow them to move quicker sometimes. So it's just a toggle option. See if it fits your character appropriately. A spaceship, for example, can probably strafe, whereas a car probably should not be strafing. Stop on overlap. Basically, the agent's radius will be except the agent's radius, the AI we're controlling, it will be added to the acceptable radius if we're using stop on overlap. If we're not using stop on overlap, it's going to go ahead and use only the acceptable radius. Now, as you saw earlier, even using stop on overlap, if you don't have an acceptable radius that is larger, because you have to take in mind your collision volume may be larger or smaller than your actual mesh, and you want to make sure certain interactions are possible. So by default, this is turned on, and it allows you, when you're using the location version, to simply have less of an acceptable radius that you don't have to adjust, and it will compensate based on the acceptable radius and the agent's radius for your AI. Basically, keep this on unless you're having issues. Allow partial path. This is our last option. Basically, if you allow this on, if it can't get to your target because it has an incomplete path, you can have this checked and it will go as far as it can before it gives up. If you have this unchecked, it will not go anywhere. Now, the important part here is our Blackboard key. Now, there's two things it can take. It can take an actor or it can take a vector, a location. And if you have it set to the actor, it's going to, well, in this case, watch, it's set to location. And if you notice me moving, it goes to the fixed location. If I have it set to the actor itself, it's going to update its target as it moves. And you notice it's now following. So that's something to keep in mind. One trick to this, however, is it only accepts actors and locations. And if you notice on here, you do not have actor. Well, you have to cheat, and it's annoying because it's hidden. If you have an object right here, down in your advanced settings, you actually have a base class. By default, it's set to none, which means it's only going to be an object. If we go back here, you're going to find I can no longer collect my player. If you want to have something that accepts an actor, be treated as an actor, change it to the actor for the base class. Now you're allowed to choose it, and you can use the actor as the appropriate Blackboard key. So, that is how you use your Move To. It's basically a very simple movement component for AI that is built into one of the built-in tasks, and it works great. If you want, you can have decorators above it or on top of it to prevent it. For example, a common decorator is here. I have isPlayerLive in my service. You can have a decorator on top of this for Blackboard, and then you can change this to, oops, that is the wrong one, because I did duration key, so we'd want isPlayerLive, and whether it's set or not, for example, or even if you have, for example, the player object, if its player object is set or not. So for example, if the player object is set, you want this to run, and it's going to run through fine. Now, in the case that my player dies, my player object will no longer be set, and therefore this will never run again. So that's one thing you can keep in mind. You can add decorators onto tasks, and something like this is very common. So, that's it for the Move To node. If you have any questions or comments, please feel free to leave them below. Hello, welcome to the video. By using the Move To node itself, and it should be pretty self-explanatory. So let's watch what happens when I have the Move To Player Object node turned on. You'll notice it goes around my barrier and moves to my player. Now if we switch this to the Move Directly Toward, you're going to notice a slight difference. It will literally move directly towards it. It will not use the AI path. It'll use the AI pathfinding to find a path, but it's not going to use it to avoid an obstacle. So as you notice, it's going to try to get to me regardless of the obstacle in the way. And of course now it's going to catch up. Nope, oh, there we go. I managed to avoid it. So there you go. That is what the Move Directly Toward node does. So let's go ahead and go over the settings. So for our settings, we have our acceptable radius. This is something you need to keep in mind. The acceptable radius is basically how close to the destination does it have to be in order for it to be considered successful. When you're using an actor as the Blackboard key, the location of your target, if it's another pawn, for example, or your player, is more likely going to be the origin or the center. It's not going to take into account the outside of it, the actual radius. So you need to usually make your acceptable radius much larger to take into account. So if you find that you're running a sequence, let's go ahead and let's lower this, have our mesh back together. Let's go have Move Directly Toward with a 5, moving to the player's location, and we run this. What we're going to see happen here is this sequence is going to run, but if you notice, it's never finishing. It's never going to trigger the next part. That's because the location it's trying to move to is in the middle of the player with a radius of 5 as the acceptable radius, and immediately when I move my character, you're going to notice it finish moving, and then it will now wait if we go over here. So that's something to keep in mind. You need to adjust your acceptable radius if you're using a location-based. If you're using a object-based, it's not usually too much of an issue. It takes the radius into account. So our next options are disable path update on goal location change. Basically, if the location changes, like for example, you saw I had the player object, and when it was chasing down the player object, it was continually updating the goal location. If you set this to true, it's not going to automatically adjust that if you have the actor or an actor as the location target. So if you want to continually path find, you would keep this unchecked. If you want to simply go to the location upon first starting, then you're going to want to check this. Project vector goal to navigation. Basically, this is just going to put the goal on the navigation mesh. You want to leave it as the default. Allow strafe. This is what allows the AI to strafe left or right as it's going towards you, rather than vertically strafe. Car more than likely would be player object or the location. Basically, the agent's radius will be added to the acceptable radius for purpose of checking the acceptable find things it's going to. It's either a location, which is going to have the advanced menu here. Under the, you will find the actor. It's going to opt and aim towards comments. Bum 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 bum. Hello. Well, I don't hear anything, but I will assure you that it is playing. Basically, the play sound task is really simple. It takes in a sound cue, and it plays the sound when you fire off the task. That's it. It is not going to delay the success or failure based on the length of the cue. It's simply going to fire it or fail, and then move on to the next part if it's successful. So I go ahead and run this. It's going to play the sound immediately, and then wait 5 seconds, and then it will play it again, wait 5 seconds, and it will continue indefinitely. Now my sound cue itself is just a simple compile sound from the editor. It only has a duration of approximately 1.5 seconds. But if you noticed, it was not delaying at all during the execution. So that's something to keep in mind. It's just intended to simply play a sound. If you want something more specific, maybe a delay, or not to finish executing until the sound is finished, you're going to need to create your own custom task node. Now, another thing to keep in mind, if you do not have a sound assigned, it will fail. It will not play none. So if we go ahead and we hit play here, you'll notice it never goes over to our next part of the sequence because the play sound node itself is failing. So that is something to keep in mind. You cannot have a blank none for your sound. You can have a blank sound cue, but you cannot have none for the sound effect itself. So if you're having an issue with play sound failing, make sure you have a valid sound cue. That is it. If there are any questions or comments, please feel free to leave them below. Bum 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 bum. Hello, welcome to the node. Let's go ahead and cover how the play animation node works and what we might want to use it for. Play animation task can be accessed by the task menu, right-clicking in your behavior tree graph, and it's one of our standard nodes that comes with Unreal Engine 4. So for settings, it's pretty simple. We have the animation to play. This can be a simple animation, or it could be any of the other asset types, animation composites, montages, blend spaces, or aim offsets. For example, we're just going to use this task animation montage. Now for our settings, by default, we're going to have looping unchecked and non-blocking unchecked. Now something to keep in mind here is these, because it's a task, until it successfully finishes, it will not move on to the next part if you're using a sequence, for example. So if you have this set to looping, it's going to continue looping unless there is an abort on it. So for example, you can add a decorator on top of this, make sure the player's alive, and maybe abort it. For the most part, you're not going to use looping hooked up to play animation. Non-blocking means basically instead of waiting for this to finish before the next part fires until we get a success, it's going to immediately fire a success when the animation starts, and then anything else can happen if you're using a selector or a sequence node. So that's something to keep in mind. If you want the animation to play before it moves on, keep it at the default settings. If you simply want to play the animation and then maybe do something else, go ahead and set non-blocking. Now to see it actually work, if we hit play, it's just simply going to play the animation, which I have currently set to very short, wait 5 seconds, and you'll notice it's going to repeat over and over. This is just a simple, easy node. Something you might want to use this for is, let's say you have an artificial intelligence and you have an alert sequence. It runs towards where it was alerted, maybe they heard a noise, it runs over there, and when it gets there, when it gets to its location, maybe you do an is at location check. Once it's at the location, play an animation for looking around. Maybe it puts its hand over its eyes and it tries to look around looking for your player. Once the animation's done, then it could go back to maybe waiting around for a second or two, or playing another animation. Maybe it calls in for assistance, and then it goes back to doing its searching for the player. So that's a useful use for the play animation. Now keep in mind, this is a very generic node. This is one of the pre-built ones, and it's intended just to simply fire off an animation. If you need something more specific, you're going to have to create your own task node itself. If there's any questions or comments, please feel free. Bum 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 bum.
Tomatoes.
Tree task, rotate to face. Let's go ahead and pull up the rotate to face node. We can right click, tasks, and it's under rotate to face BB entry. And these are going to be your default settings. Like any other node, it's going to automatically try to find a valid key on the first match once you click on it. In this case, it can go ahead and it can take an actor or it can take a location. We're going to go ahead and set this up for the actor itself, and we're going to run this and you'll see how it works. Basically how this is set up is it's going to set the player to my player every rough half second. It will rotate to face it, and then it's going to wait 5 seconds. After the 5 seconds, it's going to repeat, face the player, and wait 5 more seconds. So let's go ahead and run this. Now the green dot is the front of my AI. And after 5 seconds, as you notice, it turned to face it. If I go here and wait, it's going to go ahead and turn to face me again. And that's it. It's as simple as that. It is a very simple node. Its intention is to rotate to face your entry. Now the only real setting it has is going to be our precision. This is basically the precision in degrees in order to be considered successful. So within 10 degrees is considered success. And of course you can adjust this depending on how precise you want it to be. For the most part, it's going to hit right on the dot, but maybe you have some form of a restriction or something in the way preventing it from rotating properly, and you may need to have some form of precision here. So that covers our rotate to face BB entry node. It's useful if you want to have something, maybe there is a sound that you play, or your player causes a ruckus and alerts your enemy AI. Your enemy AI could simply rotate to face that sound, and then you could have them move to that location, and then you could have them play an animation to look around, so it gives it a little bit more believable feel. If you have any questions...
They say that boldness is for the fearless.
Bum 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 bum.
Tomatoes.
Go for what is the AI behavior here. Basically, we have our normal task behavior tree here, where I'm going to use the run behavior node, and then wait 5 seconds. Now the run behavior node is pretty simple. It simply takes in, as its only option, another behavior tree. And the goal of it is to allow you to have different behavior trees that do different things, and then basically collapse them down into a run behavior node to make it look better, to make it more compact, to make it easier to manage. You can think of it as a function or a macro by using the run behavior node. So in our example here, if you've noticed, it actually shows us a preview of the behavior tree I'll be using. And if we open it up, it's pretty simple. All I'm doing is running a sequence, waiting 5 seconds, playing a sound, and then running my custom task, which just prints out to our screen. Now, if we watch this run, what we're going to see is the behavior tree task is running, it waits 5 seconds, it gave us our notice on the top, and then it goes ahead and waits another 5 seconds. Now if we watch this, what we're seeing here, let's start over from the beginning, is behavior tree 1 runs to behavior tree 2, so that's waiting, playing, printing, running back to the top, which then finishes successfully and our second wait node fires. So that is something to keep in mind. This as an actual task node has a success or failure based on the behavior tree inside of it. So if the behavior tree is successful, then of course it's going to return a success and then do whatever appropriately. Either go back up the chain or in the sequence move to the next part of the sequence. If it fails, it will be treated just like any other task that fails, and it will restart the sequence if you're using a sequence node, or it'll roll over to the next node in a task node, a selector composite node. So let me show you that. Let me remove the sound cue. Without a sound cue, play sound will fail, and this is going to travel back up, make the actual behavior tree fail. When the behavior tree fails, then the entire thing counts as a failure, and you're never going to see our second wait. So it's going to work as expected. So we run our behavior tree and wait 5 seconds. Play sound fails, and you'll notice it'll abort, and then try again. If we actually watch in here, you'll notice these two never run, because this part here will fail when we get to play sound, and the top part aborts. So that's something to keep in mind. The run behavior is pretty simple. It's intended to allow us to compartmentalize and organize our code better and make our behavior trees maybe a little more modular. Maybe you have one behavior tree specific for finding and setting a valid target, and you can continue on. Now, one thing to keep in mind is behavior trees can share blackboards. So in this case, for example, my behavior tree for my task is using the task behavior blackboard. This behavior tree is using the task blackboard as well. So you can share the values between the two behavior trees in case you have them doing something like setting player targets or updating other variables. So that is something to keep in mind. If you have any questions or comments,
tomatoes,
what is the AI behavior? Let me go ahead and then choose either wait or wait Blackboard time in order to choose the task. These are pretty simple. The wait task simply has a wait time along with a deviation, and is simply going to delay execution and return back a success once it is done. The wait Blackboard time takes in a key, which is a float or an int, and it's going to simply wait that duration. The biggest difference is this one is fixed in the value. This one allows you to adjust it based on maybe a service setting that value. Let me go ahead and show you this. If we run through, you're going to see we're going to wait 5 seconds, and then you're going to see it immediately finish this node because our wait duration key is 0, and then it's going to come back over here. If we were to add in a service I've created called delay service, where the only point of this is to add the duration key value of 5, we're going to see it work differently. If we go and run this, now we see a wait duration key of 5. This will count down, and then this will count down for 5, and then our sequence will finish, it'll start over, and it's going to continue. So that's it. That is all your wait node is for. Keep in mind, of course, it will abort if you have something above it, like a decorator that's set to abort. And the whole purpose of the wait task, is to allow you to delay execution further down the chain. Maybe, for example, you have a move to here, and then after it moves, you want it to wait 5 more seconds, and then you're going to want it to finish. Or maybe you want that duration key here, and depending on how many enemies or your frames or other variables, or your more advanced enemies, for example, may move, wait half a second, and then look for the player, and then move again, whereas your less intelligent or your easier enemies may have longer wait times before they seek out the player. So there you go. That's what our wait and wait Blackboard time notes are for. If you have any questions or comments, please feel free to leave them below. Hello. I'm going to go ahead and I fired up a quick little example behavior tree. We have a few composite nodes, a decorator, a task, and then right here we have our example service. Now a service is going to be denoted by this greenish color, and it's basically going to determine what we should be doing based on events that are happening inside of our behavior tree and our game itself. The service is basically intended to be used for checking and updating things. Is our player still alive? If so, update the player Blackboard value. Do we have an exit we should be going to? If so, update the exit location. Do we have any ammo left? Go ahead and update the ammo count, and should we reload variable if needed? Things like that. So let's go ahead and see how we would use it and how we would create it. Services can only be attached to composite nodes. These are our gray nodes, our selector, sequence, and simple parallel, and they're easily accessed by right-clicking, add service, and then choosing one of your existing services. Your list is going to populate with any created services, as well as any Epic supplied services by default. At this time of recording, there is only one Epic supplied service, the default focus. Everything else are up to you to create and use. So creating a service, we can click on new service, and then you can choose an existing parent. You can choose one that you've created, or you can use the BT service blueprint base, and what this is going to do is create a new blank blueprint that is going to be of the service type. If you notice, the parent class is our BT service blueprint base. Now, unique things for the service blueprint. We're going to find 8 overridable functions, which we'll cover shortly, and then we'll find the service section with 2 advanced options, which we'll cover as well in a little bit. And that's pretty much it. Besides that, it's a normal blueprint with an event graph that's going to fire off the events inside of it based on whatever you have set up. So let's go and look at the example one that I've created here. This one's intent is to basically see if we have a valid pawn being controlled by our player. If we do, we're going to set our player location and player object Blackboard values. If we do not, we're going to null them out, basically. Null the object and zero out the vector. So, how do we go about doing that? The class defaults has a section here called service that basically has 2 sections we're going to want to cover. The interval and deviation, which is our tick rate, and then these extra options which determine what we're going to do while we are using this task itself, this service. The important ones here are interval and our random deviation. When we are looking at our service in our behavior tray, it's going to tell you the service example service will tick every 0.4. The service is basically intended to be used for checking and updating things. Is our player still alive? If so, update the player Blackboard value. Do we have an exit we should be going to? If so, update the exit location. Do we have any ammo left? Go ahead and update the ammo count, and should we reload variable if needed? Things like that. So let's go ahead and see how we would use it and how we would create it. Services can only be attached to composite nodes. These are our gray nodes, our selector, sequence, and simple parallel, and they're easily accessed by right-clicking, add service, and then choosing one of your existing services. Your list is going to populate with any created services, as well as any Epic supplied services by default. At this time of recording, there is only one Epic supplied service, the default focus. Everything else are up to you to create and use. So creating a service, we can click on new service, and then you can choose an existing parent. You can choose one that you've created, or you can use the BT service blueprint base, and what this is going to do is create a new blank blueprint that is going to be of the service type. If you notice, the parent class is our BT service blueprint base. Now, unique things for the service blueprint. We're going to find 8 overridable functions, which we'll cover shortly, and then we'll find the service section with 2 advanced options, which we'll cover as well in a little bit. And that's pretty much it. Besides that, it's a normal blueprint with an event graph that's going to fire off the events inside of it based on whatever you have set up. So let's go ahead and look at the example one that I've created here. This one's intent is to basically see if we have a valid pawn being controlled by our player. If we do, we're going to set our player location and player object blackboard values. If we do not, we're going to null them out, basically. Null the object and zero out the vector. So, how do we go about doing that? The class default has a section here called service that basically has 2 sections we're going to want to cover. The interval and deviation, which is our tick rate, and then these extra options which determine what we're going to do while we are using this task itself, this service. The important ones here are interval and our random deviation. When we are looking at our service in our behavior tray, it's going to tell you the service example service will tick every 0.4 to 0.6 seconds. That's because we've set up our interval as half a second with a deviation of 0.1. This is your tick time. If you want something to occur every 1 second, set it up with 1 second interval and maybe a random deviation of 0. It's going to fire every second on the dot as best as possible, obviously based on frame rate and other things. And of course, if you want it to occur more often, you'd set it to a lower. Maybe if something's super important, you'd set it to 0.2 with maybe a 0.1 deviation. So there you go. That is what the interval and random deviation is for. It's tied into the tick event inside of our service. Well, what is the tick event? That's going to be this right here. Let me go ahead and unconnect it and delete it. And we're going to go ahead and see it over here in our functions. Receive tick is basically the event that comes with our blueprint that's supplied by making it a blueprint-based service that will fire every time our activation interval fires. So every half a second with a deviation, we're going to hit the receive tick. And that's it. It's as simple as that. It's an adjustable tick inside of your blueprint service. So what are we doing here? Well, like I said, we're going to go ahead and see if we have a valid object, being our controlled pawn. And if we do, we are getting our blackboard value for our location key and setting the actor's current location to it. And then we're getting a blackboard value of our controlled pawn and setting that to the player key. If we do not have a valid player, then we're basically zeroing out our location key and setting our player object to none. So this is going to let us know whether or not we have a good player or not and where they are. Now here's a few things to keep in mind. When you are using services, if you are going to set blackboard keys, here, player location key and player key, it's kind of like a pass-through system. In here, you have your service. In here, you have your blackboard keys. Somehow your service has to know which blackboard keys you want to set based on the variables you have inside of here. Now, in order for that to happen, basically, if you are using a service and you expose variables to be public, right here, it's technically editable, but it's making them public. You'll get this little yellow or green eye, depending on if you have a tooltip filled in, and it's going to make these 2 variables public. What that does is it now allows you to set in the service a matching pair. If we go into our service, we now see our player location key, which is this value right here, is going to be assigned to which blackboard value? In here. And we'll set it up to match our player location key to be player location, and our player key variable to be player object. So now whenever this is running and we tell it to set the blackboard value, it's going to set this value here, our player location key, to obviously whatever we want it to be, which is our vector. And then when this service runs, it's going to transfer that over to our blackboard value. So that's how you get it between your service and your blackboard, or your blackboard to your service, or for example, you're doing your checks here, or your tasks need a location or an actor to go to. That's how you transfer between your behavior tree and your blackboard, making sure you have public variables and assigning them. it is very, very common if you are rushing through things, or for example, let's say we have a new selector here, and then we go ahead, okay, well, we're just going to go ahead and add our service here for, let's go with the is player live service, and then you move on. Well, it's defaulted to none, but you click on it and you don't pay attention, it's going to default to your first settings, which are player object in this case, which is not correct, obviously. I have variables like the location key should be location, player key should be object, and since this is used in a different behavior tree, I should have had another variable in my Blackboard. So it's very common if you're just adding services in and forgetting to set your actual keys, you're going to get the wrong values and things aren't going to work. So that's important. After you add in your service, make sure you click on it and set any of your default values for your Blackboard. So let's go ahead and watch this run, and then we'll be able to cover the other examples. Let me go ahead and move this over so we can see it cooperating. And let's move this over here, and here, and here, make it easier to see. There we go. And we'll go ahead and run our system. Now, if you notice, we immediately had our player, our enemy, go to our player. And if I was to move, you're going to find it follows. Now, I have it set to move to location. That's why we're getting that little jump steps. Every 0.1 to 0.3 seconds, my service is firing. It's updating the player location variable with wherever my current player is. And then that information is being passed down to my move to, and we're moving to whatever that location is. Now, if I was to go ahead and stop this, and let's go into here, and let's change our variable to something like 1 second, and play it again, you're going to notice we're going to end up with a slight delay, as our player location is only updating roughly once every second. One thing to keep in mind here, because I'm using a selector, this part right here will not fire if this part is good. And since my move to location is always good, the wait is never going to fire. So this is something we need to update inside of our playing system. Down here I have player object is set. Down here I have player object, which I'm setting every 1 second. Keep in mind it's also going to fire every time this is updating. Why is that? Well, let's go ahead and uncheck that and you'll see what happens. Wait 5 seconds, it moves, then it'll update my location after a second, and you notice how it's trailing behind me now. Well, let's go ahead and uncheck every time this is updating. Why is that? Well, let's go ahead and uncheck that and you'll see what happens. Wait 5 seconds, it moves, then it'll update my location after a second, and you notice how it's trailing behind me now. This option right here, which we had checked, which by default is checked, as you can see right here, call tick on search start. This basically, when it goes from our service to our task, this is search. This node here to here is what they're calling search, and basically you're searching for a valid task to run. When you call the tick on search start, it's going to go ahead and automatically call our tick event instead of waiting, and it's going to go ahead because the tick event ran, we'll have a valid player location and player object, and we can immediately fire this off. With this unchecked, when we run this, it's going to fail because this was not valid the first time through, and then we end up having to wait. So that's something to keep in mind. If you want something important to happen, your tick event has something important, such as setting variables, make sure you have call tick on search start so you can go ahead and set everything up the first time. Alternately, if we don't have this set, that is what our other nodes are for. The receive activation node right here is what happens when this service node is called the first time. So when we go from here to here, the tick starts timing, which means it won't fire for a second, but our activation event fires, which is right here. So for in this case, we might want to go in here, and since we know these are going to be valid, if we set this up like this, and we automatically set on activation the player's location and object, next time we run through here, instead of it failing that first time, like it was before, it's going to go ahead and run properly and find our target. Because the first time this runs through, activation fires, and activation is setting our values. So that's what your receive activation node is. It's for the first time through, you're activating the node. Now, hopefully you should be able to understand what the deactivation node is. When this is done running, basically the end play, the service becomes inactive. For example, up here we have a sequence. And we attach the sequence a wait. As long as we are in this left branch here, right here, you're going to notice, let's see if I hit the play button, this is running, which means our activation event is running and we're good. Now when this stops and we go over to this right branch, this ends. When this ends, the deactivation node will fire. So that's useful if you want to alert something or update a value. For example, in here we've moved. Now you update a variable called AI is idle. and now you know that your AI is idle because you're no longer in this side of the branch. Our last one is going to be our receive search start, which I've already overridden here. Now let's go ahead and plug this in and you'll see how it works. Let me remove my deactivate. Let me remove my activation. Let me go ahead and remove my other branch. And remember when I mentioned how the searching works, basically when it goes from here to here, we're searching for a task. So anytime this fires off and needs to find a task to run, it's searching. So this search start is going to fire anytime we go from here to here. So if we run this, you see it says hello in the top left. And then in 5 seconds, it's going to say hello again and move to our player. And now we're going to get spammed with hello. If we look at our behavior tree, we're getting spammed because we go from our root to our selector, we run our service looks for a task, so our search starts, we're running a move to, we're already at our move to location, therefore we succeed, which means since this is a selector, we're going to succeed here, this will succeed to here, and then we run it back again. So you're noticing that message spam our screen because we're constantly running from here to here. Now if I was to change this to something like a sequence, for our example, and we move, and this is one thing that's nice, is you can move things from node to node. Now we have a sequence running where after we move to our location, we should wait 5 seconds. What you're going to see happen is this right here. And it should stop, and then we'll get another hello, and then it should stop, and then we'll get another hello. And every time it's searching for which one of these to run, we're going to get a hello because this is running and searching for a task. So that is what our receive search start node is for. And those are your 4 basic nodes inside of your service graph. Now in regards to our last value here, which is our restart timer on each activation, each service has an internal tick time that is continuous. And if you have it set to restart the timer on each activation, every single time it runs through here from the start, root runs through our composite node, it activates this, it's going to go ahead and restart the timer each time. So if you want to make sure your service node is fresh, then you want to make sure you have restart timer on each activation. And of course, these can be accessed both from here, which is your detail panel, or inside of your actual details class defaults for your service itself. So that is it. That is our service node. If you notice, it's intended to do checks. It's intended to update the Blackboard. It's intended to be your key for your decorators and your tasks to give them their valid objects or locations or values that they want to work with. Services, as you noticed, it only comes with 1 by default. It's only going to be our default focus, which I'll explain in another video. And the reason it only comes with 1 is services are very unique. They're very specific to what you want done. So that's why there are no real pre-built ones. So that is our sequence node. No, that was our service node. If there are any questions or comments, please feel free to leave them below.
Wenn aus undenkbar undenkbar wird, dann wird aus mal eben einkaufen.
Bum, 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 bum. Hello, focus nodes. Let's run through our quick little example. Set and clear focus nodes. Let's run through our quick little example, and we're going to see how this works. We're going to have our little AI go to our player. Now the front part of our AI is indicated by the little round green sphere. But this time when the AI leaves us and goes back to its home point, instead of turning around and going towards it, it's basically going to retreat. The front point of the AI is always going to be facing our player when it is retreating. Once it gets back to its home point, I go ahead and I clear it, and it goes back to facing wherever it stopped at. We'll go ahead and see that in action one more time, and then we'll cover the example itself. Okay, so let's see how that is done. So inside of my behavior tree, I have 2 services I've created. One simply finds the player and assigns it to the player object. The other one only runs once, and basically if we don't have a home location, it sets a home location to the current location of our AI. So that way upon the first time run through, we know where our home location is at. Now, I've created 2 tasks and 1 decorator for our example of the focus nodes. Let's go ahead and look at the first ones. This one's pretty simple. In our sequence, we're moving to the player, waiting 5 seconds. I have my custom focus node here called set focus, and then we move back to the home location. So our custom node is pretty simple. The set focus node takes in a target. The target is an AI controller. This is going to be the controller that you're using to control this AI. And the new focus is basically what is the new focus for this AI controller. What I'm doing for that one is I'm simply getting our player key as an actor and setting it as our new focus. Keep in mind here, we basically set up the player as a key. So all I'm doing in here is closing these down. All I'm doing is getting that key as an actor and setting that as our focus. And then of course, like any task node, you need to finish executing with this success or we get stuck. So that's how we use our set focus node. Now over here, we have a decorator to see if we are focused, and then the clear focus node. So let's go ahead and do the decorator. Decorator is pretty simple. All we're doing here is the get focus actor node. It simply takes in a target, which is our AI controller, and then returns back whether or not we have something focused. Simple, that's it. So all I'm doing in this case is performing a condition check, getting our generic AI controller, getting our focus actor, and if it's true, I'm returning true, and if it's false, I'm returning false. Now after that, what I'm doing is clearing the focus, and then waiting 5 more seconds. Clear focus is another custom task, and this one's really simple. All our clear focus does is take a target, which is our AI controller. All I'm doing here is receiving the execution of our task, getting our AI controller, clearing the focus of our AI controller, and then telling the task itself to finish successfully. So as you can see here, it's pretty simple. We have our set focus node here, we have our get focus node here, and we have our clear focus node used here. And as we saw in our example, we are going to the player. After we wait, we are getting our focus, which is our player, moving, so we're staring at the player, and then once we stop, we are clearing the focus so we're no longer staring at the player. Now if you want to see some of these in action, let's remove the clear focus. What you're going to see here is, after he moves to his home point, he is now going to stay focused on our player, and he will continually watch them. So before I could move around and it would stop, now you'll notice he's constantly tracking the player. That's because I have a focus target set, using the set focus target, and I'm not clearing it. Once you set the focus target, that is where your AI is going to focus at all times until you clear it. That's why I have the clear focus here. And all I'm doing for our decorator is basically getting to make sure we have something focused, just so we don't run this branch for no reason. If we aren't actually have anything focused here, let's say for example we don't focus, then this branch won't run because this is going to fail. So that's it. Those are our 3 focus nodes. They are intended to give your AI a focal point, so that way when it is moving or it is stationary, it has something to focus on. It's going to automatically rotate and focus. That's the entire point, because what you're going to do is, if you don't use a focal point and you try to do it yourself, you're going to find setting the controller rotation is going to fight with the actual focal point for your moving, such as your move to or your move forward, and you're going to have issues. So set your focal point, use your normal move to nodes or your AI move tos, let the focal point do its looking. If you have any questions or comments, please feel free to leave them below. Oh, welcome to the video. For a quick little example here, you're actually going to see an AI spawn from across the way, and then he's going to run to me, and then he's going to go ahead and stop. And then he'll follow every few seconds and try to find me again. Nothing really special about this. However, what I'm having to do is, in the play for my character, is spawn in his default controller, get the AI controller, and then go ahead and set up a blackboard for my AI to use. And in order to create the character, I'm using create actor right here, spawn actor from class, and I'm setting it up to spawn my generic AI character. Now the video is about spawn AI from class, so let's cover that. Spawn AI from class is a node that was created to facilitate spawning AIs. It's meant to automatically spawn the controller for the AI itself and set up any behavior trees you want, rather than having to set up all the other complicated script inside of the AI itself. So let's remove the script from our AI, and in our spawner class, let's hook up our spawn AI from class node. We're going to go ahead and set up my generic AI character, and I can actually just go ahead and hit play, and you'll notice the character spawns and comes right at me. Now to make it more realistic, I need to get actor location, and make it so it actually spawns at my spawning sphere, and there we go. And you can see it comes after us, and it looks identical to before, no difference. The difference being behind the scenes where we've actually used one node, the spawn AI from class node. So let's look at the settings. By default, it's going to come set up and nothing's going to happen. And if you compile it, well, it's not going to give you an error. It's just going to generically spawn nothing. We need to set up at least one thing, the pawn class. This will be the pawn you want to spawn, usually having an AI character as the parent, if I was to pull this up. We're going to find this as a character, and inside of our character, we have a AI controller class set up. So that way, when it spawns in as an AI, it's going to automatically assume, and it's going to spawn an AI controller and set it up based on this setting. The next one is our behavior tree. This is optional. As you saw, I didn't use it, but if you have a behavior tree you'd like them to use automatically, rather than creating one and assigning it during the spawning of the character, we can go ahead and set it up here. We just go ahead and select one of our behavior tree assets, and it would go ahead and run that on the start. Now the other options are pretty simple. The location to spawn it at. Since I have a spawner, I'm simply spawning it where my spawner is. The rotation, if you want to adjust the rotation, and then a no collision fail check. This is pretty simple. If my spawner was, let's say, where's my spawner? Right here. Let's put it down here and hit play. You'll notice, well, we have an issue. My spawn is going to have a problem because it's inside of a collision. If we do no collision fail and we move it up enough, let's move it to something like that, our spawn is going to have no issues because it's going to spawn and ignore collision. So basically, when you spawn, if there's something colliding, such as you're inside of a box, let's say, and that box would prevent collision, would prevent spawning normally due to collision, if you check this, it's going to basically ignore it when you spawn it. And that's pretty much going to wrap up the node. We have a return value, which is like anything else we create. It's going to be a reference to the pawn that we created. And we use this node to spawn our AI. Whenever you want an AI to spawn, automatically possess its AI controller, and then use an optional behavior tree.
Bum 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 bum.
Tomatoes?
Hello, welcome. Quick little example. See a small little issue there? When he repeats, you'll notice once I move out of the way, he will continue moving. If we look at the top left, it'll say whether we've been successful on moving or not. So we are using the move to location node. This is part of the navigation system, and it's using the AI controller in order to move. Let me go ahead and pull up the node itself somewhere where I have some room. And you'll notice that when you type in move to location, it's not going to come up. That's one thing. You have your simple move to location, and that's going to use your navigation system, and it's not going to require anything special. It's a basic move to. And then you have things like your new task, move to location or actor. The move to location is actually under move to location with a target of AI controller, and if you're not pulling it off of AI controller, so that's why unchecked context sensitivity, you're not going to find it. So let's look at the default version of it. It's pretty simple. Here is the simple move to location node, and here's the full move to location node. You'll notice quite a difference. Simple move to simply takes in your controller and a goal. The move to location actually takes in an AI controller reference, so it's different. It actually will only run with an AI controller. This will run off of a regular controller. And you have your destination, which is going to be a location, just simply somewhere in your world. Everything else here are optional settings that you can use to fine-tune, and your biggest difference here is you actually have a return value letting you know what happened. Did it successfully find a path, or did it fail because it couldn't get to the location? So let's go ahead and look at the node. We have our acceptable radius. This one's pretty simple. How far away do we need to be before we consider we finished? We were successful. Stop on overlap. You have your pawn. In this case, it's going to be my enemy. Your pawn has a physical size. It has a radius that is it's the radius. If we were to look at my generic AI character here, it's this radius of the capsule here. If we're using the stop on overlap, it's basically going to add the pawn's radius to the acceptable radius. So in this case, because we have this checked and we have this as -1, it's going to take the radius of my capsule component, which is going to be 34, and I gotta stop clicking on the wrong things, and it's going to add that to my acceptable radius. So basically, as long as we're within 33, that's when it's going to call the stop. Use pathfinding, I'll show you in a second. Basically, it's whether or not it should use the pathfinding on the navigation mesh, or if it should just go straight to the target. Project destination and navigation. Basically, it's going to project it onto the navigation mesh. It's useful for debugging purposes. Can strafe is pretty simple. Your character, when it's moving, is forward or turning and moving forward. Strafing is your left and right strafe movement. And it's whether or not you allow your AI, when it's trying to get to my target, to maybe go forward and strafe around a corner. It gives it a little bit more smoother motion, but it's up to your desires. Filter class pulls up a navigation query. These are more advanced topics. If you have some navigation filters for your pathfinder, you cannot go completely to your target. If you have a partial path, it's acceptable. Try to get as close to you can. So let's look at this in use. I've got all the default settings, and when we run it, you'll notice our character moves around and stops. And you'll notice that they're not exactly going to the exact location. My character is stopping them because my character's radius. So that's why they nudge forward a little bit. If we were to adjust our acceptance radius to something like 30 and hit play, you'll notice they're going to stop a little bit farther away, and we're not going to have too much of an issue. Stop on overlap, let me uncheck that. We'll hit play. We'll run through, and you'll notice our character kind of pushes us out of the way. Use pathfinding. Now if you watch what happens when I hit play, you'll notice the AI goes directly towards me and kind of, well, in the case of this, because of this area here, this wall, he's not going to be able to get to the location because the wall's in the way, and he doesn't know how to use pathfinding or the proper navigation. If we were to put that back on, whoops, pathfinding, there we go, and run it, now you'll notice he can properly go around any obstacles. Can strafe is whether he can strafe, we discussed that. He's going to turn around the corner, as you noticed there. If you noticed, he went straight forward, turned, and then went forward again. Can strafe means he's going to go ahead and basically slide across and come to me. Filter class we're not using, and then allow partial path we really don't need because I have full paths to get to the target. Now, one of the biggest differences, like I mentioned, is we have a return value here. This is going to give us a path-following request result, long name, enum return value, which as you can see here I'm printing out. On the top left you can see request successful. You'll see it again, request successful. And then when I jump across to my non-navigatable part, you'll see failed. So you can use that to determine if you should be doing anything based on your return, if you could actually move properly. Our previous simple move does not have a return type, so it basically fires and forgets. Now this one does fire and forget, but the biggest difference is you can actually do something based on if it could properly path. On this one you'd have to actually check and see if it was moving or if it had the ability to path, and you have to do a bunch of things like that. So that's your biggest issues on there. So that is going to wrap up our move to location node. Remember, it is just a more advanced version of our simple move to location. We have the ability to return back a value if we were successful or not, and it can take in some more options so you can fine tune. Keep in mind, it does take in our AI controller as a target. So in this case, what I did, because this is inside of our character, is I said, hey, go ahead and get a reference to yourself, or our character, and then get the AI controller that our character is using. In this case, it's going to be my generic AI controller, which I've already set up, and then it's going to feed that in as the target. So the move to location talks to the AI controller and sets up the navigation and pathfinding.
Bum 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 bum.
Welcome to video 4. What is didn't set up, so let's set it up, and we'll walk through how I've set it up. Basically, I am having a move to actor example event inside of my character, and I'm calling it when I spawn in my controller. And my controller is going to talk to the move to actor node here. And when we run it, you'll see our little guy moves to our actor, and then he'll stop. And because I'm using a move to actor, he will continue following my character until he successfully gets to it, or is unable to move anymore, like you can see here. So let's go ahead and take a look at it. Our simple move to actor is our basic node. It takes in any controller and a goal, and it moves the actor. The move to actor node, without the simple part, is slightly different. It takes in an AI controller, not just a regular controller, and it takes in a goal. Then you have a bunch of... Let it run. Finishes. If you notice, there's no completed node here. That's
Bum 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 bum.
Welcome to video 4, and it's pretty simple. We have an AI that simply goes to our character. If I move my character, it'll go ahead and try to find him again, as you can see here, and it uses basic pathfinding. And if I get off the edge, it's not going to be able to get to me. So which just simply moves somewhere. Features such as if we're doing overlapping or if we're doing pathfinding and things like that. And then we have our AI move to. The biggest difference with our AI move to is this is an asynchronous task that is going to fire off events based on if it was a success or fail. If we look at the other nodes, we only have one output. Something's going to continue, and then our AI maybe gets to the destination, and hopefully it's good. With the exception of our move to locations, which give us a return value when we fire off, we still don't know if it made it to the destination or not. That's where AI move to comes in. We actually have a success and a fail pin. But we don't have any real big options here. Those are up to you to use. So let's look at the node. Let me disconnect this. It's pretty simple. We have a pawn. This is our controlled. This is going to be what we're moving. What has AI that we're moving. Now if you notice, this says it needs an AI controller to move to a specific location. If I was to plug in a player, like for example, my player, and I told it to do an AI move to, it's going to fail. It's not being controlled by the AI currently, so nothing's going to happen. Because I'm spawning in this character with an AI controller, it's fully ready to go when I tell it to do something. So our pawn goes inside of our pawn input. Then we have two options, a destination, which is a fixed location, a vector 3, or a target actor. Like our other move to nodes, if you set up a actor as the destination, we'll run this, it will continue to pursue until it gets to the actor. if you set up a destination. So let's do get actor location. And let's plug this into the destination instead. And we hit play. It's going to find that location when it fires off, and it's going to move to it. So if I'm here, it'll move to here. Even if I move later, it goes to that fixed location. So that's something to keep in mind. Destination cannot be changed. It's going to be a fixed location. Actor is an actual actor object, and it's going to continue on until it gets to within an acceptable radius. And that brings us to acceptable radius. How far away are we going to be before we are determined at our target? If we set this to 0, for example, and we run this, we're going to find that when it gets to us, well, it's good. It's close enough. It doesn't have to have a big radius. If we change it to something like 200, you should notice a pretty large area. And we'll go ahead and you'll see, boom, a stop of 200. These are nice for, let's say, example, you have a melee character. You might want it to be within melee range. You set a smaller acceptable radius. Or you have a ranged character, maybe it fires a gun or a bow and arrow, that has a radius of 200 units. So you can set in an acceptable radius to that value, so it'll stop out of range. And it'll be really annoying because then the character has to go chase it. Stop on overlap is just a boolean that basically adds in the pawn's radius to the acceptable radius to prevent it from overlapping and basically going 0 to 0 on the destination location. By default, you'll probably want to keep that on. It helps where, like, the biggest things that I'm doing, executes, getting the downset execute cached. It's not every time. Now the first time is success. And it makes sense if you think about it. Our movement result, this node here, is only updated on a success or fail. But it will basically store the last result, so it's something to keep in mind. If you get a movement result on your execute wire, don't count on it being valid. Simple as that. Count on your movement result being valid on a success or fail being ran. And in this case, when I succeed, it'll give me a success node. And then when we fail, you're going to see on failed, aborted at the top. Because it aborted the movement. It was not able to move because it could not find a valid path. That's why you'll notice if I get it right and I jump across, navigation path fails immediately. It can no longer navigate. Even though there's navigation mesh left, it's updated at real time, and it's going to fail immediately because it could not bridge the gap. Because I do not have anything here it can get across with. It's always going to be right. You need the AI want the chain. Our AI successor give you
Bum 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 bum.
Video 4. What is get random point in navigable radius? So this is our node here. It allows us to use our AI navigation system and get a random point in a radius. So if we run our example, we can see in the top left, I print out where our character is going to when they move, and we can see this little yellow sphere that indicates the location where they're going to. And if we were to close this, let's go to here, we'll run, we're going to eject, and then look at our layout and pull up our navigation data. You can see the green is our navigation mesh, and you can see our character running to one of the locations. So it seems simple enough. Let's look at the node. The node takes in a vector for the origin. So in this case, I'm grabbing where our AI player is and getting something around him. That's the radius. So the radius in units, how far around them to get a point. The other two options are optional. We have a nav data. Generally, this is going to be the world nav. It'll grab your default navigation data, have your navigable area based on the filter class. Now, once it finds a point, it's going to return that back out as a vector, and it's going to return back a Boolean. True if it was correct, false if it wasn't. What does this mean? Well, there's a couple things. Let's say, for example, it finds a random point in the radius, but there's an error. It's going to return back false. So you probably want to check and make sure you have a valid location before you actually work on it. Now, there's something to note here. You've noticed while we've been running this, it doesn't seem like we have a problem. The issue is going to be actually in the fact it's a navigable radius return. So I have a few cubes here. Let me pull these up. They're a little area, basically a set of walls. And you'll notice when I redid that, it rebuilt my navigation. Now when I run this example, we're going to eject out, and we're going to look at it. You'll notice our point is here, or here, but our character, well, they can't get to it. However, our point that they're going to try to get to may be in an area they can't reach. That is something to note about the get random point in navigable radius node. It doesn't necessarily give you a point in an area that you can get to. It will just simply give you a point somewhere in your navigable area. And you can actually see on the top here, I have a navigable area on the top of these walls. It may even return a point that's there. So you can get back a point from this node that is completely unreachable by your current character. So keep that in mind. And that's it. That is what our get random point in navigable radius node does. Note, as of right now, there's a change in the master source code that switches this node from a pure node to a callable node, so something that's going to have an execute in and out. So if yours doesn't look quite like this, or it's changed to get random location in navigable radius, it still acts the same, it just looks a little different.
Bum bum bum.
Leave it alone. Basically, it looked fine. We could reach. You can see another. Now, if we rebuild size radius area, and that's basically it. That is our get random reachable point in radius node. Takes in where we want to start it from, some radius around that, and gives us a location that our character is going to be able to reach from this origin within that radius.
Hier, ich habe einen.
Hello.
Hello everyone, welcome back to my Unreal Engine tutorial series. So today I'm going to recreate my enemy AI using behavior trees, and the first step would be this enemy character will select some random location around him and go to that location and wait a bit, and then he will continue the same like this. Now he waits and wait, and then he continues. Now again wait. So I'm going to implement this simple behavior with behavior trees. And this episode is sponsored by this moment. I have been using this AI human AI controller, which I have defined by just like a normal blueprint. So I haven't used any of the blackboards or behavior trees here because I was kind of reluctant to use them, as I felt like that was too much work at the time. But since I got a couple of requests to do the same thing that I have done with my this AI controller blueprint using behavior trees, I'm going to give it a try. So okay, let's get started. I'll create a new folder called AI. So I'll put everything related to behavior tree and AI here. So first, instead of this AI controller, I'll create a new AI controller. It's not listed here, so then I'll select blueprint class and controller. Okay, I select this. Right, now I'll name this one AI. What is the name I used before? AI human, right? This is also AI human PT, because I'm using behavior trees this time. Okay, and also to work with this, so this is the AI controller. Here we don't have anything yet. So now we need to define two things to set up behavior trees. One is behavior tree and the other one is blackboard. So this is behavior tree. I'll call this one human, PT human. So this is the behavior tree, the so-called behavior tree. And also we need another thing, blackboard, BB human. So this blackboard is sort of like I can create variables here, and we can use, modify, do stuff with this behavior tree. Okay, let's see how we use it. Okay, now first thing is, in my AI controller I need to tell which behavior I should run. I can do it like this, run behavior tree, and here I can select this BT human. Right, now I'm going to do a simple thing. So all I'm going to do is select some random point around the character and go to that point and wait a few seconds and then go somewhere. and I have set up everything like now mesh and character here. This is the same character that I have been using throughout my tutorial series. So okay, now this is the new AI controller, and I'll select this character and assign AI human BT instead of AI human. And if I play this, it is not doing anything at the moment. It's just a dumb character who can't do anything. Right, now this is the root of the behavior tree, and if I drag a line here, I can see three things. So selector, simple parallel, sequence. I'll select sequence for now. So here from left to right we can define some tasks, and this AI controller will execute those tasks from left to right. And by default I have these tasks: make noise, move directly to word, move to. Okay, so I'll do move to, and here I need to give the target location. So to define the target location, I need to define a Blackboard key here. So the target location is should be a vector. So I'll create a vector. I'll name this target. Okay, and now I can select. Oh, wait, I can't select yet. Okay, so first I need to define. I need to set this move to variable. I can do it here. Here we can add a new service. A service is something like a function that we can use to update these behavior tree keys. So I'll add a new service, and by default it is named like this. So I'll go here and I'll name this one SRS set location. Set location, set move target. Hello everyone, behavior tree, the so-called set this move to this, and by default move target is receive event receive activation AI. So this will be called whenever we call this set move target service. I'll compile this. Now here I can add this as a service as set move target, and here I can get a reference to controlled pawn. Get controlled pawn, and then I can access get actor location, and I'll get some random location around this character, and reachable point in radius like this. And for the radius I'll give 2000, and I'll set the output of this value. I need to set it to this move target. So to do that I need a variable to access that. So the variable should be in the type of Blackboard key selector. I'll name this one BB key, and then set value as vector like this, and compile. Okay, but still I can't see. This is invalid. Alright, yeah, here when I haven't select, I have selected the root or nothing, I have to set the Blackboard asset. So I have to set this BB human, and after that I can set. Alright, and here as well. And here when I select the set move target, I don't have a way to select which key I should update. I need to update this move target key, but still that's not visible, just like here. That's because I have to set this one to instance editable and compile. And yeah, now I can select the key, and since move target is the only key I have to select that. Okay, and after that I'll wait 5 seconds, it says here, and and also I'll add a deviation of 3 seconds. So I will wait some random time after 5 seconds, and that means plus or minus 3 from 5 seconds, and then I'll select another random location and restart again. Let's see how it works. Okay, he went over there and stopped, and yeah, he's going again somewhere and stopped, and again he's going somewhere and stopped. So I'll show you. Yeah, here, since I have selected that AI controller, I can preview it. So now he's moving. Let me put it like this so that you can see it. Where is that guy? Where did he went? Oh, right here. Okay, now you can see this guy is now moving, now waiting, and now moving, and now waiting. Alright, I'll stop here for today, and in the next time I'll look into my code like this point. Hello everyone, welcome back to my Unreal Engine tutorial series on behavior trees and enemy AIs. So this enemy I have here, in this episode I'm going to show you how to create a patrolling path for enemies. As you can see, this white line defines the patrolling path for this enemy, and this enemy will go along the patrolling path and go here and go back there and go from here again and go back there, like that. And also this asset is Castle Fortress, which I got from the marketplace. And if you wonder, okay, here is the demonstration. And also please note that this asset, this fortress asset, will not be included in my source code because I don't own it and I don't have the permission to share it. So this is how this enemy works. You come here and go back there. This is his patrolling routine. Okay, in the project file update, you will only have the enemy AI and my character and other things that I have developed. Hello everyone, welcome. Okay, in the project file, not the Castle Fortress asset. Okay, so first I'll create a new child class of this CH enemy type. I'll name it CH enemy patrolling, because I need several other things like some spline to define where this character should be patrolling, to define the patrolling path. So here I'll add another component, a spline, like this, and I'll name it patrol path. Okay, and for now I'll make it like this. Compile. Okay, now here I'll delete this character, this CH enemy, and add this CH enemy patrolling character. Okay, and now you can see the patrolling path like this. I'll place this character here as the starting position. Maybe I'll rotate it like this. Okay, and click on this point so that you can make this spline longer. And here is another patrolling point. And after that, I'll add another spline point here and select this one again and make it like this. So now this is the patrolling path. And I'll select right click here and set this spline point type to linear so that you won't get that curve, because this curve is not necessary. So right, what I need this character to do is come to this side and go back to here and come back here. So continue that behavior basically. Okay, now we have the patrolling path. Now what I should do, let me open my Blackboard and also the BT human behavior tree, and here I have defined this set move target. And here what I'm doing is I'm getting the actor location and get random reachable point. So instead of that, I want some point on the patrolling path. Okay, so let's see what are the interfaces that we have in CH enemy. Actually this extends the ch human character damageable inputs. Right, so now what I'm going to do is this. I'm going to create another interface like this bluprint interface, and I'll call it PPI NPC. And here I'm going to add a new function, get next target. Now get next location. So basically what this does is returning the location that I should go next. Okay, and there should be an output like this in the type vector, and I'll name it target location. Compile, and now here instead of this one I'm gonna call get next location using this PPI NPC of the control pawn and plug it like this. Now in order to work this, I need to implement the NPC interface. I'll implement in the ch enemy like this, PPI NPC. Alright, now in the interface I have this get next location method I just defined, and now I need a way to get the patrolling location. For the general type of enemy, that means the normal ch enemy does not have a patrolling path, so therefore I'll just get actor location and return of enemy, that means the patrolling location. For the general type of enemy, that means the normal ch enemy does not have a patrolling path, so therefore I'll just get actor location and return random reachable point in radius. So the normal enemy will randomly go about the world within the radius of 1500, and I'll override this get next location method in the patrolling enemy. Where can I override this? Right, I have it here, get next location. I'll override it like this, so I don't need the parent function call here, so I'll just delete it. And here I'll get the patrol path, and we have to do one more thing. Let me show you why. So this is the patrolling path, and if I simulate the game, okay, you can't see that now. Let me explain it. So this is attached, this path is attached to the player, so as the player moves around, the path also moves around. So I don't need that behavior because I need the path to be persistent even when the enemy is moving. So therefore at the begin play, can I do this in the construction? Let's see, detach from component. Let's call this detach from component so that it will be detached from the parent character class and it will stay in the same place as I move the character. I'll keep everything in the world. Alright, now let's see. Still it is moving. Well, yeah, I can show that this patrolling path stays still when the character is moving by doing this. Here I have attached a cube at the end of the path, okay, and when I am in the game editor, you can see that cube is moving when I move the character. And if I do this detach from component here, okay, wait, I need to keep world everything. Right, now when I move the character, the cube still moves, but if I play it, and even if the character is moving, that cube stays still, but we can't see the spline because spline is not a visible actor, but the spline also stays still. So I think it is safe to assume that. Right, now I'll delete this one, that's only for demonstration purposes. And here, as for the AI controller class of this patrolling enemy, I'll set C AI human BT. Okay, and here I have this get next location. Okay, so here I can get some point along this spline like this, get location at distant along spline, and the coordinate space is world, and distance is at the beginning. I'll put 0, so I'll promote this to a variable. I'll name it patrolling distance, and I'll do this. I'll do a branch. If patrolling distance is smaller than the length of patrolling path, get spline length. If this is smaller than patrolling path, I'll set patrolling distance. I'll add another 200. Is that not enough? Okay, let's try 500 to the patrolling distance and then return it. And this distance difference is, and this is what I am going to return. I will place it like this. Okay, so if this is false, well, actually I don't really need a branch. All I need is this. I'm gonna select based on this. If this is true, that means I am not I haven't exceeded the patrolling path length. So if this is true, I'll give plus 500, otherwise I will give minus 500. That means I should come back from the end point to the beginning of patrolling path. And also we have another case. So what if patrolling distance is smaller than 0? So let's check that state as well. If this one is smaller than 0, let's do another, let me duplicate this one. If this is false, I should keep returning minus 500. If this is true, I should return plus 500. And condition is this. So then again, if this is false, I should return whatever the output of this one. And if this is true, I should return plus 500 no matter what. And the output is this. Okay, so this is all I need here, I think. Right. Now, in the set move target, I have already set up that. Get target location and set it as the blackboard key of move target, and this is the behavior tree. Yeah, here this is wrong. This must be minus 500 and this must be plus 500. Okay, let's see how it works. Plus 500. Okay, let's see how it works. I'll start playing from here so that I can see what, oh wait, what the other character does. Okay, there's the enemy, and he's coming here. Actually he's running, that's not good. And also he's stopping at each point. Let's fix them. In here, in the begin play, I'll call this toggle run. I'll do a toggle run, disable target itself, and also in the behavior tree there is a 5-second gap. I'll make it 0 because I don't need it to wait anywhere. Okay, let's play and see what happens now. Okay, now the enemy is coming here. Let's see if he turns and go back. Okay, he's not turning. Why is that? I get it. Problem is here. And this in this selection, because whenever my patrolling distance returns go back or smaller than the spline length, I return plus 500. That's the problem. So I guess I would have to go back to using a branch. Sorry about that. And also we need another variable. I'll name it distance change, and default value I'll put plus 500 or 500, and let's do a branch. If this is less than 0, I'll set this distance change to 500, and here instead of this one I'm gonna put distance change. And this condition alone is not enough. This must be smaller than 0, and in the else, this false branch, I'll add another branch like this. If this patrolling distance is not smaller, this time I'll check larger. If this one is larger than spline length, I'll set patrolling distance to minus 500. Otherwise, don't do anything. Okay, let's see how it works. Okay, there is that enemy is coming, and if I'm correct, he should come to this point and go back to the starting point and come back again. Alright, now he turned and going back. Alright, and yeah, that's all for today. And if you would like to support my work, you can get the membership of my Patreon club. Link would be in the description below. Also, I have uploaded. Hello everyone. So this time what I'm going to cover is this. So as you can see that patrolling enemies come in here along the path that I have defined, and at the end of the path he's going to wait a little bit like this, about 5 seconds, and then he's going to continue patrolling routine. So now again he will go to this point and wait a little bit. So just like this, you can define points that you need this character to wait, so that player will have opportunities to pass, sneak out some areas, or some opportunities to make a plan and play the game. So again, this guy will wait at this point for some time before continuing. And to implement this behavior, I'm going to use behavior trees and wait time, and also some services, behavior tree services, to update wait time. And as always, this episode is sponsored by these generous Patreons. Thank you very much for the support you guys are giving me. Okay, so in the current implementation, this is how it looks. That enemy character continuously walking a little bit. Well, actually what I have to do is, when my character reach the end of the path or some point, some specific point at the patrolling path, this wait time should be more than 0 seconds. So first, instead of this wait, there is another node called wait blackboard time. Alright, so I'll delete this one, I don't need it anymore, and I'll define a new blackboard key in the type of float wait time. Right, now I can assign that value here. By default it should have 0. Well, there is no place to define that, I think. Okay, now I need a way to set this wait time. So in here, in this set move target service, I'm getting the target location through this npc PPI npc blueprint interface from the enemy character, as I have defined. Hello everyone. So this time what I'm going to cover is this. So as you can see, and here for for the patrolling enemy, I have overridden it here. Right now, when one of these conditions happen, so that means I am at the end of the patrolling path, as I have explained in the previous episode, because this direction change happens when I am at the end of the path, either at the beginning or at the end. So in both cases, I should wait a little bit before continuing to walk. So actually, the simplest way would be I could add another return here as the wait time, and then I could get that wait time here like this. I have get the target location and set the blackboard value as a float. But if I do that, because this function name is gets next location, so this function kind of does not express that it also returns the wait time as well. That is not good in terms of programming practices, because it kind of makes this function like less cohesive. I'm not sure the exact term, but it's not clean. So therefore, I'll here define a new variable, because it kind of makes this function like less cohesive. I'm not sure the exact term, but it's not clean. So therefore, I'll here define a new variable is at end. No, I'll name it patrol checkpoint. So here, because end and the beginning should be a checkpoint in the patrolling path, so here I'll set patrol checkpoint to false, and here set patrol checkpoint to true, and here as well. Alright, now in the interface of the NPC, I'll define a new method. Just like get next location, I'll define get wait time, and output should be float wait time. Okay, so now for the enemy, get wait time, it can be any random variable, random number, because it's not patrolling. So I'll set a random float in a range between 0 and 5. And for the patrolling enemy, I need to override get wait time like this, and I don't need the parent node. So wait time should be selected based on if it is a patrolling checkpoint or not. So if it is false, I should return 0. If it is true, I should return, let's say, 5 seconds. And here now I can add a service. Well, I need to define a new service now. I'll name this one S. No, I'll name it S for service. Oh, get set wait time, and open it. And just like before, I get the event receive activation AI, and get the control for get wait time through the BPI NPC interface, and I need to set the blackboard key. So for that, just like before, I have to define this BB key variable in the variable type blackboard key, and name it BB key. Should be instance editable. Set blackboard value as float, and the value should be wait time. Compile. Now I can use that service. Add service S wait time, and the blackboard key for this one should be wait time. And let's check how it works. My enemy started to come, the patrol enemy is coming like that. Let me toggle debug camera. Right, now he should wait here a little bit, 5 seconds actually. Alright, now he's going back. So this kind of mechanisms we can use to create opportunities for players, so that a player can observe that this guy wait at the end of this point or at some points for about 5 seconds, and that time window can be used to pass that area or do some planning and play the game accordingly. Okay, so that's all for today. In the upcoming episodes, I'll continue to improve this AI system and also AI fighting, attacking, and stealth. Hello everyone, welcome back to my Unreal Engine tutorial series. So today, what I'm going to show you is this. When the player character go to the sight range of this enemy character, he will equip the weapon like that. And when I go out of his sight range, he will put back the weapon. Here is the demonstration. So basically, I'm going to start working on sight configurations of AI enemy character. And this episode is sponsored by these generous Patreons. Thank you very much for the support you guys are giving me. Plain enemy, blueprint, right. And yeah, we don't have to add anything there. I'll just open AI Human BT. And here, I need to add a AI perception component. Like this, I'll name this one AI perception sight, and here as I'll add, suppose under the sense config, I'll add AI sight config. Sight radius, yeah, I'll keep these things as default values. And here I have detect enemies, detect neutrals, and detect friendlies. And as I know, this detection by affiliation part is not fully supported with blueprints yet. So therefore, I'll enable everything. And I'm going to use my isEnemy interface function that I have used before to determine whether it's a friend or foe. So yeah, let's get started like this. On target perception updated, I'll add this one. And I'll just print something like this. Append, get the actor name, the actor that I am seeing through my sensors, and I'll break this one. And stimulus successfully sensed. See, I'll print this like this so that I can see what happens with the sensors of my AI character. And if this is working, what should happen is this. So when my enemy character see the player character, it should print to the top left corner of the screen actor name space C true. If the enemy NPC character lost the sight of the player character, it should show the character name space C space false. Let's see if that works. Hello everyone, welcome back to my Unreal Engine tutorial series. That works. Now I'll go here, and as you can see, it just shows CH player C true. And when I go out, it just shows CH player, and as you can see, it just shows CH player C true. And when I go out, it just shows CH player C false, like this. Okay. Also, I should mention that I have already added AI perception stimuli source to this player character. That's why it can already seen by the AI characters. Otherwise, it will not be able to see because this player character will not be registered as a source for perception system. Right. So now here, I also have implemented this isEnemy function here. Like this isEnemy function, I have already defined this in a previous episode through the interface of this PPI character. Here under fight, I have defined this isEnemy blueprint interface, and I'm going to use the same thing here in order to identify the character that I'm seeing as an enemy or not. So I do it like this: isEnemy, get the actor, enemy, and the team number. For the team number, I should return the team number of current actor. So I can access the current actor like this: get control phone and get team. This is also a function that I have defined in the character blueprint interface like this, and I'll show you this get team function as well. I have defined it here and implemented it here. So just team is just a integer number that I have defined in the human class, human character blueprint, like this. And for the player this would be 1, and for enemies this would be 0. Let me show the player as well. Here we got many variables. Team, yeah, team number. Actually I have given 2, not 1. So if the team numbers are different, in this EaseEnemy function it will return true, and also if the character is already dead it will return false, because we should not identify dead characters as enemies. Okay, so ignore those parts if you, this dead part, if you haven't followed my previous tutorials. Right, now here get the enemy, get if this is the enemy, and do a branch. If this is true, I should print this, and also I should I'll create a boolean variable like this. You can see, no, enemy C, and I'll set like this. Wait a minute. Yeah, if I define the variable here, then it would be harder for me to access this variable from the behavior tree services. So therefore I'll define that variable in the ch enemy class, just like this, enemy C, and by default it should be false. And to set and get this variable, I'm gonna need another interface function. I'll define it in the VPI NPC interface. Set enemy C, input should be boolean, and also get enemy C. Now you might wonder, why do I always add these interfaces and make things complicated? But trust me, this is easier. When things get complicated, it is necessary to do it like this. Otherwise you will have to do casting everywhere, and and then you will have unnecessary dependencies between your code components. So that's why I keep doing this, even though it looks like a little more work at the beginning, but trust me, it will be useful later. Okay, see, right, now here I'll implement those interface methods. First I need to compile this. Okay, so get enemy scene, I had to return enemy scene, and for set enemy scene fight, I'll add another graph AI here, set see set like this. Right, now this will be connected like this. Get the control pawn, set enemy scene, and set it and compile. Also connect this. Right, now, and also another thing, so when my character see an enemy, he should equip the sword. So I can do that calling this toggle weapon interface function that I have defined here, and this is also another function that I have implemented in one of the previous episodes. You can refer to that if you want. So yeah, I'll just call that function here like this, toggle weapon, and equip or not should be based on I can see or not the enemy like this. And for the target I should use this same get control pawn like this. And let's see how it works. And I'm not going to further implement this behavior tree, I will look into that later. For now, yeah, for now I'll keep the enemy. I'll stop running the behavior tree because I don't need it to move. I only need to demonstrate how to use the site config. Okay, so let me play and see check. Right, now as you can see, the enemy is unarmed because he haven't seen any other enemy of his. Now when he see me, he equipped the sword like this. Now I'll go back out of his sight. Now he should put back his weapon like that. Okay, I'll stop here for today, and the next episode I will show how to make this character follow player when he sees Hello. Hello everyone.